a week ago. And they're like, aren't you worried about de-anonymizing the blockchain? Not really, just because if you think about it, Google was de-anonymizing. If you use that logic, Google was de-anonymizing the internet when they built their search engine. The data's already there, so I don't really feel like I'm screwing with anybody's anonymity. There's probably other people doing this a lot better than me. I have no idea. But it's good for people to kind of think about these kinds of things when they write about it or when they make transactions. It is important to know that any transaction that you make on the blockchain ledger is going to be recorded forever and everyone can see it. It's harder to figure out who owns a wallet, but it is certainly possible that people are going to write analytics like this for whatever purpose. So this database allows us to ask any question of the blockchain. It allows us to figure out who has the most unspent Bitcoin. Where is the Bitcoin at? Who has the most money? How much money was spent in a day? What is the average money? It allows you to correlate with stuff like the stock market. It allows you to correlate with stuff like current events or any other economic issues. And that is basically it. Oh, crap. Anybody have any questions? Yes? Oh.
Two things for the timestamps.
Yep.
First of all, how detailed, how in-depth? Does it go nanosecond? Does it? I was just curious.
So the question, do I repeat the question or do people have the question? You don't have to. I don't have to repeat the question. So the timestamp is in Unix epoch timestamp, which is seconds from when the block was mined that the transaction took place on. So how precise? I would give it a margin of error of 15 minutes. Because that's the average time period. So it's harder to correlate exactly when it happened, but you basically have about a 15-minute window of being right or wrong. And that's just because that's the average time that it takes to have a new block. 10. Oh, it's 10? Shit, it's 10 minutes. Thank you. And you said you had another question?
Yeah. Does time zones like have anything to do with it?
So time zones do not have anything to do with it because the way the Unix epoch timestamp works is it's only the number of seconds that have taken place since July 1st, 1970.
Okay.
So, but I guess, what did I just say? January 1st, 1970, but I don't know what time zone. Okay, yeah, GMT, so.
It allows some variance.
Say again?
It allows some variance.
It allows variance?
Time basically in the future, as long as it's not too far.
Okay. For when you start mining, like on the blockchain or with the?
If you were to do the transactions right with the timestamp, you can put future times too.
Okay.
It just accepts it as long as it's not like too far.
Okay.
I forgot what the number is.
Okay. Cool. Thank you. Cool.
Thank you.
Yeah. No problem. Any other questions? Yes.
So when you were showing the hex dump, is it like like looking at a packet header where you know these particular bytes are addressed, these particular? Okay, so that's always static, and you can parse that out. Could you then, if you wanted to track a specific person's transactions, socially engineer them by just saying, hey, I heard about you losing your 15 mil, wanted to give you some bitcoins, and then now you've got their address to query against them?
Can you? So you're saying
like tell him you're donating to him because you feel bad for him losing his 15, see what address you just donated to, and then use that to then run against his data to say who else took from or gave to this address.
So you're saying just asking him for his Bitcoin wallet.
Hey, I want to give you some money.
Yeah, you could do that, but the thing is, it's trivial to introduce new Bitcoin wallets. So you don't have to reuse, and it's actually best practice to use lots of different Bitcoin wallets for anonymity and whatever purposes.
Okay.
Yeah.
Thank you.
A new address for every transaction. Yep, is the right way to do it. Best practice according to experts.
And then
yes.
Based on that question, there is like a known attack vector that I guess the darknet operators look out for, and is basically where somebody gives dust transactions, so a few satoshis, so that you can pin that address and see where the money flows, so where it ends up. So there's like complicated addresses that take out like basically tainted inputs and basically let those not move out. Because like when you saw the inputs and outputs where it's basically by Satoshi, Satoshi's level, like basically how many Satoshis were in there, because there is people who basically spam the network with Satoshis, hopefully being able to track it. And then the base 58 was basically so you could double click the address and then be able to copy and paste it without it breaking with punctuation.
That makes so much sense.
Yeah.
That makes so much sense. I figured it was either that or something with the QR codes where like maybe but that, yeah.
Yeah,
that
it was
makes way more
basically
sense.
that, and I don't know why I'm thinking this too, but I don't remember exactly. The copy and paste I do was so when you had capital O's, like you had lowercase and no zeros, so you don't confuse them.
Oh, yeah, sure.
So it was like back in the original design, but it is a pain to work with.
Yeah.
Then there's this project out there called Blockseer that does like something similar, but with graphical relationships. So you can actually see the input outputs.
Okay.
And then my question was, how big was the actual data set after you put it in the database? So like that.
How big was it on disk after it was in the database?
Yeah.
Oh, like how much did the database reduce it?
Yeah, like what is the size of like the database? Like yours, if you were to basically focus on keeping it as an on-chain, or sorry, like basically what's the current status of it?
Yeah.
Type model, like how big is that?
I don't know. I remember it being very close to the size of the CSV. So the database that I used didn't seem to compress it at all or do anything like that. So basically, I had an 80 gig or I had a 100 gig CSV, and when I loaded it in and I looked at that directory as it was loading in, I have to get back to you on specifics, but I remember it being about the same size as the CSV.
Do you remember, was it less than the full 80 gigs?
I don't remember.
All right.
I'd have to go back and look.
I was just curious.
Yeah. I know there's other stuff like, Cassandra would reduce the crap out of it if you had really rigid data types and stuff like that. But ClickHouse, I didn't have as much experience with, and also I tried to read a lot of the docs. It's mostly in Russian. So like I would go and I search like, is there compression? And I find like one Google Talk post of a bunch of Russian. I don't know what.
They give you a link to some other.
Yes, another link to another Russian format. I don't know what the fuck any of this means, man. You're really not helping. But yeah. Yes.
So is there anything in the blockchain protocol or whatever to stop like maybe me having two wallets and just transferring one Satoshi back and forth?
There is a transfer fee.
Okay. Cool.
So the way that works is basically, this is going to get into a lot of other stuff, but basically there's a finite amount of Bitcoin that can be mined. And eventually when all of those, by design, when all of those Bitcoin are mined, the Bitcoin network will be powered and Bitcoin miners will be rewarded specifically by fees. So a transaction fee is extracted from every transaction, and it pools together to actually then reward the miner once Coinbases are gone and once once mining new Bitcoin, once all the Bitcoin are in circulation. So to answer your question, yes, there is something preventing you from doing that. Cool. Any other questions? No? I'm done. My name's Andrew. Thank you guys so much for coming to this talk.
So this is the ground truth track at BSides Las Vegas 2016. Thank you all for being here. I just want to mention that our sponsors are awesome, and we couldn't do this without them. So you should all make sure to visit some of their booths out in the chill area. Let's see. This is a live stream, and it's recorded. So please turn off the ringers on your phones. And oh yeah, and also the area in the back is a fire lane, so we have to keep that clear. So please, if you go out and come back in, don't stand back there. Okay. So we have Ryan Peters and Wes Connell from Blue Vector. Ryan Peters is an applied data scientist, and Wes Connell is a threat researcher. All right? So give it up for these two. Thanks.
Thank you. By way of introduction, as he had mentioned, my name is Wes Connell, and I am a threat researcher and software systems security guy with a firm called Blue Vector. And alongside me is Ryan Peters. His official title is Applied Data Scientist, but I've been working with him for a few years. He's a superhuman software developer, machine learning expert. He's also a diehard Cleveland sports fan, so he hasn't stopped smiling since Kyrie drained that 3 in Game 7. And if you're from Golden State, I apologize. I'm from DC, so I know heartbreak quite well. At any rate, Blue Vector develops technology to address pervasive network security challenges. And along those lines, we do a lot of analytics, and machine learning is one of our core competencies. And the manner in which we have operationalized machine learning can be much more broadly applied to solve countless problems in the security space, which brings us here, and that's what we'll be highlighting today. So the agenda is as follows. We will briefly review how cyber defense capabilities have evolved over time. We will highlight this common model problem that exists in not only machine learning deployments, but across all security solutions. From there, we'll demonstrate an attacker's perspective of defeating this problem with persistence. I'll hand it off to Ryan, and he will introduce a moving defense solution through data diversification, which adds an element of uncertainty to the attacker's perspective. We'll review this moving defense from concept to practical implementation to quantitative results. And the results are numbers. It can get pretty dry, but they're really important. So just stay with us. We'll then summarize everything, provide final takeaways, and we'll wrap things up with a quiz at the end. I'm just kidding. The quiz is in the middle. No, there's no quiz. So here is what the security landscape looked like 30 years ago. Not a whole lot going on. So given the non-existent defenses, attackers didn't have to work particularly hard to wreak havoc. And so the Morris worm in 1989 got the ball rolling, followed by an onslaught of viruses in the 90s and even through to this day. And so in response, antivirus engines surfaced. And they were and continue to be a very reactive approach in that you can't write a signature for a sample that hasn't been released or seen in the wild before. And along those lines, we had packet and stateful filters that were deployed in the form of firewalls, which became the standard. We had exact hash matches on files and packet filters that were limited to exact matching on IP address, port, and protocol. If you had a firewall, you were deemed OK. And so antivirus and firewalls eventually gave way to sandboxing, emulation, and virtual detonation. And they're fantastic in that they provide in-depth and detailed behavioral context while also recognizing malicious indicators. And unfortunately, as most of you know, there's no shortage of sandbox evasion techniques. In particular, you've got malware that has environmental checks for signs of a sandbox. You can look for common analysis tools, check for mouse clicks, mouse movement. You can check if the CPU has multiple cores. You can check the disk size. You have arbitrary sleep statements. You have exploits that target only specific versions of Flash Player and PDF viewers. And we're also seeing varying methods of persistence. And typically, malware will bootstrap itself to load and execute its system startup. But we've seen as recently as last month, the APT28 hacking group would persist their payload when the user opened a Microsoft Office application. And so in general, it's just very difficult to scale these technologies, given that we are drowning in data today. So today, the attack surface has now grown and expanded and evolved, and we're seeing everything from nation-state sponsored attacks to point-of-sale attacks, insider threats, social engineering, and especially today, it's ransomware. And so users and enterprises are demanding additional protection. Here we are again, and the security industry must respond and adapt. And so what does our security posture look like today? We've got machine learning. And many vendors would say this is where we are, this super tech robot. And that machine learning, a technology from the future with a power that may mark the beginning of the end for the human race, solves all of our problems and is totally unbreakable. Woo! That's right. Yep. And so in reality, we're probably here. Okay? So machine learning has added this new dynamic. And it's far less brittle, it's much more robust, it's dynamic, it's proactive. But the weaknesses vary depending on the implementation. So let's take a deeper dive at how machine learning has been deployed across the security industry. So we break it out into a couple categories here. Across the top, we have supervised machine learning, which entails labeling the data that you're training on so that the model has an understanding of the differentiating characteristics. And then we have unsupervised with no labels, and they're merely clustering algorithms that attempt to find structure in unlabeled data. On the opposite axis, we've got incremental, and we've got batch, and incremental learns continuously. It continuously integrates new data. And you've got batch algorithms that train all at once. And so in this top left category, we have a few things: user behavior analytics, insider threat detection, and it's deemed incremental generally because it's building profiles over time. And it's unsupervised because we are identifying outliers and anomalies and departures from what's normal. And occasionally we'll have this network anomaly detection in the supervised arena if known examples of bad behavior are available for training. In the top right, we have network traffic profiling, which are generally supervised and incremental. And an example would be users labeling a stream of emails as being spam or not spam. In the bottom left, we have this it's unsupervised batch. We have malware family identification. And it's generally unsupervised because we are using clustering algorithms to find structure in the data. And again, it's batch because we generally build these on very large libraries of malware. And in the bottom right is our forte. It's malware detection. And it's almost exclusively relied on with supervised batch algorithms, where the training is performed on large corpuses of data that are labeled as malicious or benign. So we'll be fixating on this for the remainder of our talk. So with that, let's take a closer look at supervised machine learning. So here, we have the supervised machine learning overview. We are collecting malicious and benign data in the top left, and we create these feature vectors, label them appropriately, and then we pass that off to the machine learning algorithm, and it generates a classifier or a predictive model. So if you are a machine learning practitioner, this is a simple concept. If you are not, this concept can be intermediate to stupid difficult. So we're going to dumb this down a little bit. So let's pretend we're building a model that distinguishes Hollywood celebrities from software developers. Okay, so the training data for Hollywood celebrities would include people like Ben Affleck and Matt Damon and Brad Pitt. And these feature vectors, these representations of who they are, would be things like tall, dark, handsome, shredded, dating supermodels, 8 figures in the bank, stacks on stacks of cash. And on the complete opposite side of the spectrum, you have software developers, people like Wes Connell and Ryan Peters, and Joe and Sean, and most, if not all of you. And these feature vectors, these representations of who we are, would be things like tall, skinny, socially awkward, goofy looking, terrified of public speaking, hooked on Pokemon Go, or probably on Reddit, developing carpal tunnel one workday at a time. And so these are two polar opposite classes of people. And it's going to be a damn good model. And so we pass these feature vectors, these character traits, and their appropriate labels, celebrity or developer, to an algorithm, and that creates a model that should have no problems distinguishing these two groups of people. We deploy the model, and it will try to distinguish these developers from celebrities based on what it knows. And so instead of building a model that distinguishes developers and celebrities, we're building one merely to distinguish malware from benign content. So are there any questions before we press on? Okay, great. So we have a couple potential vulnerabilities of machine learning. Number one is we have training set manipulation, so within this malware versus benignware model. One example would be if a web scraping source gets popped and begins serving malicious content, resulting in incorrectly labeled training sets. Another example would be a malware author that designs malware that resembles benign software. And another example would be inserting benign strings into malicious programs, and we see this happen very commonly with things like putty. Number three is that you can have malware authors that manipulate their sample to avoid being analyzed altogether. This can be things like obfuscation, bit shifting, maybe putting their payload in a password-protected zip so that the model never even has access to it. But if we take a step back, there's a vulnerability that all malware detection technologies are susceptible to, including current implementations of machine learning. And we refer to this as the common model problem, where we share identical signatures, rule sets, engines, models, emulators. And so I want you to imagine that each user or enterprise is represented as a building here, and each is seeking to keep intruders out. And so they go to the town lock store, and they buy a lock, and that lock is a representation of a security solution, right there. And so intruders interested in breaking into one of these targets can ensure a swift, silent, undetected entry by knowing how to break the lock before they show up. And under the common signature-based deployment paradigm, everyone in town is protected by an identical lock because they're using the same set of signatures. And in most cases, an intruder can just visit the locksmith and buy a lock for himself. And so he takes the lock home, he works away at picking it, breaking it, free of risk, time constraints, or any neighbors noticing. And so the idea here is that an attacker can easily verify that his exploit will be successful against a target that's protected by such a signature-based solution. And because all deployments are identical, all the attacker needs is to obtain any copy of the signature-based product and iterate against it until he learns how to evade detection. So those were the earlier solutions, particularly antivirus. What about newer approaches that use things like emulation and sandboxing and heuristics? Well, we find ourselves in the same predicament. Each deployment is the same, even though they're stronger locks. And again, because all these deployments are identical, all the attacker needs is to obtain any copy of the heuristic engine or sandbox or emulator and iterate against it until he learns how to evade detection. So keep in mind, the attacker doesn't need to understand the inner workings of the security solutions. He just needs his own copy to test with. And so how about machine learning-based security solutions? We have this super robust, dynamic, proactive solution, but we're seeing the same problem here. We are still distributing the same identical lock to each individual enterprise. And so it's no different. Let's see if a malware author in possession of a machine learning-based security solution can evade detection, and in this case, we're going to try it with obfuscation. And so the workflow here is pretty straightforward. We're generating a payload. For our lab, we were using a reverse TCP shell. So when the victim gets infected, it spawns the shell back to the attacker. And then we are obfuscating it. We use Shikata Ganai encoding and a handful of others, but again, the emphasis is not the specific payload or the encoder or the tooling. The point is that the attacker is working to evade detection and bypass the controls in place. And this is through obfuscation. So generating the payload, using the randomly selected encoder to hide and obfuscate what he's doing. He's embedding it into a calc.exe template. And then he's testing against, in his lab, that copy of the AV and the machine learning. And so in our lab, we use the AV software ClamWin because it's free and open source. And then the model that we built was built using a supervised machine learning algorithm with scikit-learn. And we trained on 20,000 benign and 20,000 malicious portable executable files. On the right-hand side, we have our test list, and this is data, the training data that was held out so that we could test against to check how effective our model is. And it had a 3.5% false positive rate, which means it was flagged by our classifier, but it was not in fact malicious. And almost a 4% false negative rate, where it was not flagged, but it was in fact malicious. And so again, we have to assume that the attacker has access to both AV and machine learning software in order to do this. And so the antivirus solution is looking for an exact static signature. So permuting the file until the signature is evaded is pretty straightforward. And in our experiment, the attacker only had to obfuscate his payload one time before evading detection. And so again, the machine learning solution is pretty robust. And so obfuscating could actually increase the likelihood of the malware sample being detected. And while the payload is being obfuscated, the calc.exe sample could be missing characteristics of benign-ware. Not only it's hiding its malicious intent, but it's also that's absent of benign characteristics. And so in our example, the attacker had to obfuscate over 1,900 times before he was able to evade detection from our machine learning model. And so the attacker here is in the driver's seat for two reasons. Number one is that he's confident the model has not changed, as most vendors only deploy new classifiers a handful of times per year, per what's common with batch learning. And he's confident that all targets have the same model. Therefore, if the attacker can defeat one instance or one copy, he can defeat all copies. And so all it takes is persistence. So if we take a step back, let's revisit this lock analogy and see how we can do better. With machine learning, locksmiths make newer, stronger, really robust locks. But unfortunately, he's still selling the same locks. And so the problem here is pretty obvious. It's not necessarily to build stronger locks. It's that we should be using different locks. And additionally, they should be changed every once in a while, just like passwords. And so machine learning is well suited for implementing these dynamic, moving defenses. And this is mostly due to the vast number of independent variables that we are able to control. We've got the feature space, as I demonstrated, the learning algorithm, the data input, and it can be accomplished in an operationally realizable way. And so why hasn't this been done before? Well, for one, it's very difficult to implement, and you can imagine it's a logistical nightmare. And most importantly, how do you verify that each lock is different across these different enterprises, yet equally effective, and still find a way to distribute and maintain them? And so it's very costly, and it's not discussed among vendors, as it's easier to just produce one model and share it with everyone. And so by altering the machine learning model so that it's unique for each deployment, we can achieve this moving defense. And again, these defenses should be changing over time. And to discuss this moving defense solution in greater detail, I'm going to hand it off to Ryan.
Thank you, Wes. So let's look at how we can implement a moving defense solution using machine learning. So as Wes mentioned earlier, there are three main knobs that we can really turn to change our machine learning model. So the first one is the feature space. So the data will look different to the learner depending on which features were used. But the problem is, in the lab, we're choosing a feature space because we believe it to be the optimal feature space. And it's really hard to maintain efficacy if we're forcing ourselves to use a suboptimal feature space. In addition, we lose the ability to describe samples as feature vectors if each deployment is using a different feature space. The second knob we can turn is the learning algorithm. But the problem with this is there are a limited number of learners available. And it's also extremely difficult to maintain efficacy, as some algorithms might be more suited for a classification problem like malware detection. And it's also pretty cumbersome on the vendor to have to develop unique solutions for every single customer. The third input that we can use, or the third knob rather, is the data input. And if you change the data, there's really almost no bound to the number of different classifiers we can produce. And by fixing the feature space, we allow our data to be represented as feature vectors. So we're going to choose this knob to turn in our moving defense solution. One thing we haven't discussed yet are the practical issues of where this training will actually take place. Does it take place back at the vendor's lab, or does it take place wherever the machine learning model is being deployed? So centralizing with the vendor would be fairly difficult, and you might have to send data back to the vendor depending on where you're getting that data from. So we're going to assume moving forward a distributed model, where the permutations are happening locally on site with the user. But it's important to note either of these would accomplish our goals. So how can we construct these classifiers to achieve a moving defense? Let's first look again at the current machine learning for malware detection paradigm. Let's peer into the locksmith's workshop. So back in the vendor's lab, we're curating a large, benign, and malicious library. There's often terabytes of data, millions of samples. The vendor's adding their secret sauce, their feature space, the algorithms that they've selected, and they're training the learner to recognize differences between samples. And the result is a black box classifier, or your lock. The vendor then pushes that classifier out to the user environment, and then the classifier is exposed to unknown samples and issues determinations as to whether it believes it to be benign or malicious. But it's important to note here the samples here, represented by yellow circles, are still yellow because there is no ground truth available to the learner, or to the classifier model. And different classifiers might make different determinations on the same sample. And this is a concept we're going to be revisiting later. So if we want to generate a new lock, it's fairly straightforward. We can just use a different set of data. We can then push out that new lock to the user and repeat the process as necessary. So the question is, what is the best way to instantiate a moving defense in practice across many user environments? We see that by using different data input, we can generate different classifiers. But here are many possibilities on how to actually vary that data input. So the simplest approach is we can just use the vendor as a data source. We could sample the vendor data in some intelligent manner. Maybe there's different algorithms that we could use, or age off old data. But the main problem is we're drawing from the same source, so we're really lacking some diversity. And it's likely going to produce locks that are not that different from each other. And it's also unlikely that the vendors are going to be willing or able to provide this service. They'd have to curate a lot of data, and if they have the data anyway, why are they not including it in the original base model? So we can do better. So the second option is we can use a local data source for the user environment. So we're using data that's uniquely seen by that deployment, and we're feeding back the data labeled by this classifier back into the data set. So this does make the classifier unique, in particular to your local data, but it's only reinforcing what the classifier already thinks it knows. It's reinforcing imperfect knowledge. And if we actually peer under the hood here, we see that the classifier is getting some of the classifications wrong. So it's just reinforcing the errors. So again, we can do better. So the third option is we can still use a local data source, but we can feed back only the errors, and this will require correctly labeled samples. So this one's going to require trusted analyst review. But often these adjudications are already being made when using the security tool. So what we would be doing is adding knowledge users are already generating, but has been previously untapped by the learning model. And the resulting classifiers are going to be tailored to that user environment. They're going to be stronger on the content they are seeing. But more importantly, these classifiers are unique, and now everyone is using their own locks. So we're going to select this option for the remainder of our talk, and we're going to call it in situ learning, which is named for the locality of the data source. So in situ means people are not just able to buy different unique locks, we are actually making everyone a locksmith. So this in situ concept is actually pretty simple, but there's many different factors to consider when operationally implementing this idea. So here we're going to discuss two different dimensions, balanced versus unbalanced, and replacement versus addition, to consider when determining how to incorporate additional local data into the training set. So the first option we have is balanced replacement. An equal amount of the benign and malicious training set is replaced with new data. You have unbalanced replacement, in which you only replace samples in one of the old training sets with new data. Balanced addition, equal amounts of new data are added to both the benign and the malicious training sets. And unbalanced addition, in which you only add new data to one of the old training sets. So why would you want to choose one versus the other operationally? You might want to balance the addition of your data to prevent the classifier from favoring one class over another just because there is more of it. However, a slight unbalancing might not be a major issue, and you might be able to deal with this issue with whatever learner you've selected. But it definitely could be a concern as more and more data is added. You might choose a replacement approach if you want to more quickly balance that model to your local samples. But you're doing that at the cost of losing part of the original training set. And if you choose addition, you're preserving the original training set, but you're increasing the time required to train your new models. You might be increasing storage requirements for these new samples. So we tried all 4 approaches, and when you're only adding or replacing up to 20% for a single branch off the base model, we actually did not see a significant difference in performance. So we're going to choose unbalanced addition for this experiment because it's the easiest to implement operationally. It doesn't require additional samples or feature vectors to balance the training set, which is something that the vendor would likely have to ship to a user. So let's look at some efficacy results for this unbalanced addition approach. So the top row of this table is the performance of the original base classifier. If you remember from earlier, it was trained on 20,000 benign and 20,000 malicious PE32 samples from the lab. This local data column, the false positives, these are the files that were missed by the local classifier. So it's going to be 100% to start off with because we missed all the files we missed. So if we add 1% to the benign training set or 200 benign files, the false positive rate falls to 14%. Adding 2% or 400 benign files, it falls to 8%. And this trend continues as more and more local data is added to the original model. Therefore, we have shown here that adding local data previously missed by the base classifier to an in situ model results in lower false positive rates on that local data. So how far has this performance deviated against the original lab test set? A different classifier is not really a better one. Excuse me. We want to make sure that we did not significantly bias from our broader test set. And as the results here show, there was little to no degradation in performance on the lab data. Therefore, the in situ models we generated are performing equal or better than the base classifier. So we can extend this by generating 10 random classifiers using 5% unbalanced addition and evaluating the performance. And you can consider this similar to a k-fold validation. We ultimately want to prove that we're not just getting lucky with the specific sampling of the new data set. So we can take the original lab data set and add a random sampling of local data missed by the base classifier. And this will produce classifier R1 or trial number 1. We can repeat using a different random sampling, which produces classifier R2 or trial number 2, and so on and so forth for R3 through R10. It's important to note that while these classifiers were generated using the same local data source for this experiment, they represent 10 different operational environments, each with their own data sources. So if we look across all 10 classifiers here, we're seeing fairly consistent performance. Standard deviations for false positive, false negative rates are about 0.5%. So the main takeaway here is we're generating classifiers with equal or greater effectiveness compared to the base model. In other words, we are producing equally effective locks. But the question remains, are these locks fundamentally different from each other? Okay, so we're going to use 2 different metrics to try and capture model similarity. So the first metric we're going to use is what we call feature space commonality. And this is more specific to our implementation of machine learning models. So when we're training our models, our total feature space was down selected in the lab from a global feature set. So we're going from potentially millions of samples or millions of features down to tens of thousands of features. And only a subset of these features are actually going to be used by the learner when we're generating a new model. So we're defining the commonality here as the features used by both the base classifier model and the in situ model divided by the sum of the features used by each model. And the results show about 30% of the features were used by both models, which means 70% of the features used by the model are different or unique to that model. And we see the results very consistent across all 10 of these models. The other metric we can use is what we call overlapping misclassifications. And this is a more general approach and can really be applied to any machine learning algorithm. And so we know every classifier is going to make mistakes. What we're looking to capture is if the in situ mistakes are the same or different compared to the base classifier. So we're going to use a consistent test set for all these classifiers. And the subset misclassified by each model, which is about 3% of the files, are shown in the circles of this Venn diagram. So the commonality here is going to be the samples missed by both the base and the in situ model divided by the sum of the samples missed by each model. And the results show only about 50% of the samples missed were the same between the two models. And again, these results are very consistent across all 10 models. So using these two metrics, we're pretty confident that our in situ models are significantly different from the base model. But are we just forking these models in the same direction? Or are they being forked in different directions? And so what we really want to look at is how the in situ models differ from each other. So we can answer this question by simply looking at a pairwise comparison of all the randomly generated in situ models using our misclassification metric. So there's a lot of numbers here, so let me explain first what's going on instead of focusing on exact numbers. So let's look at a comparison of R1, classifier R1 versus R2. So we established earlier that R1 is different from the base, and R2 is different from the base. So what we're trying to answer here is how R1 differs from R2. So the forward slashes here represent the files missed by R1, which is going to be about 3% of the total samples it analyzes. And the backward slashes are going to be the files missed by R2, or about 3% of the total samples analyzed. And the intersection of the slashes are the files missed by both classifiers, which end up being about half of the 3%. And we can repeat this comparison for R2 and R4 and so on and so forth. What we see is for any two given in situ classifiers, we have roughly a 45 to 50% overlap in the misclassifications of the 3% that each of them miss. So half of the time they are missing the same files, but half of the time they are not. Again, it's important to re-emphasize here that each in situ classifier represents different deployments. Therefore, we are gaining diversity across all of these deployments. These locks are not just different from the original lock, but are significantly different from one another. So let's summarize the benefits of in situ. First, we have that diversity of defense. And this is both spatially, which is across deployments, and also temporally. If you got hacked on August 1st and they got access to your classifier model, you could retrain it on August 2nd and incorporate even the data that was used to hack you. So this really increases the uncertainty for the attacker. Second, we're generating environment-specific classifiers. As we showed earlier, we've increased the performance on the type of data that's observed in that environment. And these results are consistent with performance improvements we've seen in enterprise environments. The third is we have increased responsiveness to new threats. So previously, if you missed a file, the only way to improve the classifier was to submit it to the vendor, cross your fingers that the sample gets incorporated into either a custom model from the vendor or ideally the global model. But often you would have to rely on short-term solutions, which could potentially be indefinite. These included things like brittle signatures or rule matching, whitelisting. So an approach like in situ allows data to be incorporated into the model immediately as dictated by the user. And the fourth one is one that we didn't really touch on. With this approach, since we're doing it on-site where the machine learning model has been deployed, there is no need to share personal or proprietary data. And again, this is not an argument against data or threat intelligence sharing in general. Regardless of the desire to share or whatever technical hurdles that might exist, some situations are difficult or even illegal to share certain types of information without excessive modification. So for example, you might have PDF files with personally identifiable information, PII. You might have health records, proprietary company info, or classified data. So an approach like in situ allows this data to be incorporated into the machine learning model rather than having to discard and rely entirely on the vendor's data or the vendor's willingness to implement a custom solution for your environment. So summarizing the big picture, improvements in machine learning methods for malware detection are weakened by the reliance on the traditional deployment paradigm. a dedicated attacker, as we showed earlier, only needs a copy of the security solution to break through the target with confidence. Secondly, the concept of a moving defense addresses the shared model vulnerability and may be naturally applied to some machine learning solutions. We discussed just a few of the many different ways of achieving a moving defense using machine learning and settled on several design decisions that were easiest to operationalize and yielded the best results. And third, the diversity offered by a moving defense is better for the herd. And by better for the herd, we mean if we are all using identical defenses, we are all worse off for it. Users should engage with their vendors about its implementation. So I'm going to leave you with this one thought. Changes in the security industry don't just come about because of changes in tactics of adversaries. Users must demand change. So we challenge you to gain more understanding of the underlying technologies in our security products, in particular the problems with them, and to continually challenge commonly accepted practices across the industry. Thank you very much. So now we're open for any questions.
If people have questions, could you just queue up on the microphone
So I remember the part where you're talking about the different ways you would change the training data to achieve the different models. I think I maybe misunderstood something about like how you're choosing the different learning algorithms and winding up with the different classifiers though. Could you touch upon that?
Are you referring to this slide here? Or are you?
Well, I guess like at a high level, I see how the differentiation of the training data could give people different models.
Correct.
But ultimately, because we're all still working from the same base and at least a subset of the attacks are the same, I am having trouble seeing like how this doesn't just lead to one person having a really diesel protection if their attack surface is novel versus everybody else who would have a more standard thing because only the data is changing in some slight ways maybe, or?
I mean, that's true. You're going to get a variety of defenses, and the better for the herd sort of comment was more referring to, we don't know an attack happens until someone actually gets popped. And the reality is, machine learning is a probabilistic approach. And so if we can at least move some of those defenses to catch that, it helps out the herd by, educating them of new threats. I don't know if that answers your question at all.
I guess just like, how are you also switching up the learning algorithms? I see
Oh.
you're switching the data.
Yeah, we're not switching up the learning algorithms because it would cause too many issues. There's a limited number of learning algorithms that are available.
It's just training the model differently to look for different features because the features of the data that was local to that environment has been recycled into that classifier on site.
Yeah, because
It's not just the data that's changing, it's the features that you're looking for.
Yes.
well, yeah. So I mean, the feature space that we're going to extract from that file or that sample is going to be the same, but the features that are actually used by the learning algorithm are going to be different. And so that's where you get a lot of your diversity in the, that's what really results in a lot of the changes in classifications that you're seeing.
So did you generate any attacks against the machine learning models and then test the, well, we'll call them vulnerabilities against the machine learning models and test them against the different models that you generated, the in situ models? When Hiram spoke earlier, he said that in their experience, changing even changing the type of model, once a vulnerability was found, it tended to apply across model types from neural nets to decision trees to whatever. And so did you actually test against any vulnerabilities to see if changing up the in situ model actually prevented the vulnerability?
Yeah, so I mean, that malware variant that we showed earlier, we sort of shortened the demo part here, but we tested that against our in situ models and found that about half of the models now caught it, but half of them still missed it. So it's fairly consistent with what we've seen.
Okay.
So.
Okay, so that was actually part of my question as well, as
Sure.
how that calc sample with the...
Yeah, we should have included that slide, that sort of
it's
circle
okay.
back, but
And
yes.
then, but then my other question is, this is fascinating work, this is awesome.
Thank you.
One of the things that kind of occurred to me as well is, and I want to pick you guys' brains about it, what if you just had one model that you were incrementally, like always updating, like with the unbalanced additions, but like every time you got a new sample to scan, the model was always getting changed or whatever.
Yeah, so I mean, there's a lot of continuous learning algorithms that are out there, and I think a next step would certainly be looking into those algorithms. We haven't really spent much time looking at those.
Yeah.
But that would also address your issue of again, it requires, it's the same barrier of an analyst has to adjudicate it, and so you can assign it labels. But I do think that's a good idea, looking at continuous learning algorithms.
Cool.
So, thank you.
So this, in one way, is a follow-up to the previous question.
Sure.
You talked about false negatives,
Yeah.
malware that gets in but isn't detected.
Yes.
How does the analyst know to add it back in if it hasn't been detected? We know from the Verizon studies, I think it's 18 months, 24 months, that often malware is in the organization, and before it's, someone notices that there's some malware there. So have you thought about how to get those false negatives back into the loop?
We've seen a few examples where larger enterprises, after they've gotten popped, they go do the forensics and curate a list of all the malware they've seen. So they kind of house that, and so if we give them the capability to develop their own models, they can funnel that in from the get-go. But after they've been popped, it's tough.
Yeah, that's the billion-dollar question there. If we can,
Yep.
So that's a hurdle you hadn't thought about how getting over, the lag between infiltration by false negatives and then the discovery of that false negative.
No, that's a very tough question. This approach certainly lends itself better to false positive reductions. And that's really important because the analyst workload can be pretty hefty if you have high false positive rates on your classifier algorithm. So but even just feeding, we showed we were just even feeding false positives in here. We didn't do false negatives that we had separate experiments where we were doing false negatives. But in this case, even just feeding false positives, we got diversity in both the malicious files it missed and also the benign files it missed. So.
I think the key to making inroads.
Why don't you come up to the mic, Dave?
Yep.
It's your question.
Behind that.
It just kind of occurred to me that maybe the key to making inroads along the billion-dollar question is sort of the, I hate to say virus total approach, but crowdsourcing, getting all the samples you can, just constantly feeding this thing, whatever it is.
Yeah, I mean, you can think of some, there's some creative, sharing approaches that we could look into. If you had trusted groups that were willing to share these samples with each other, you could still get the diversity without having to actually communicate with the vendor. So there's a lot of different, this road goes down pretty deep if we, look into potential ways to share data. Okay. Thank you.
Thank you for your talk. That was good.
Thank you.
I have a question. I actually am a vendor who's trying to build a product in this area.
Okay.
And this is amazing how people are talking about it, and we are talking back in the lab as well.
Sure.
And I'm founder of the startup. And my background is ArcSight, which most of you guys probably know. The challenge that we see as a vendor is, like you said, that the algorithms can be built, but the data is different for each environment. And when we try to train the model, we need access to that data, and which becomes a bottleneck for us. Because, like you said, you can't share everything, but when we talk to customers, they'll be like, show me the demo, I can't see my data. So how do we break through that challenge and work together on that?
Do you want to talk to feature vectors?
Yeah, I mean, so one of the benefits of using this approach that we selected is we can abstract our data as feature vectors. And that's not to say that feature vectors, the features that you extract might have some personally identifiable information in them, but you could design them in a way where it's completely anonymized data. So in that way, a user could share data back to the vendor without actually sending the samples, and it wouldn't be you could avoid those issues. So I think that's one avenue that could be used.
Alternatively, you'd have to give them the capability to use to generate a model locally with their data without sending anything back. But
Yeah, and that's one of the
certainly
reasons
that
why
can
we
be.
chose that, or we talked about that distributed approach, because they don't have to share any data, even feature vectors, back with the vendor, and it really becomes specialized for their environment.
Great. So I am looking for people who want to participate. Give us your data. We will provide our services and train the model to detect these attacks. If anybody's interested, let me know. I'm in the room.
Cool. Thank you.
Thank you.
Alrighty. Well, I think that's it. Thank you guys very much. Appreciate it.
Thank you very much.
events happen. So please, visit their booths out in the chill out area. Want to mention that there's, we're live streaming this and recording it, so please turn off your cell phone ringers and stuff. And yeah, I think standing in the back is not an issue, but just so you all know, the back is a fire lane. Please don't stand back there. Okay, so up next we have Pablo Brewer, who is the director at the Center for Information Warfare and Innovation. All right, thanks. Give him some applause.
Hey, thanks. Thanks for coming out. So I'm going to talk to you a little bit about snake oil and how we're going to live with snake oil and the fact that it may be okay as long as you realize that you're buying a little snake oil. So mandatory disclaimer: these views are my own; they're not that of my employer. Not mandatory disclaimer: vendors are fine people. So if you're a vendor, please don't await me with pitchforks and torches after I'm done with this talk. They're InfoSec professionals, just like the rest of us. They got to make a They do the best they can developing products, but they at the end of the day they also need to make a buck. So last time I gave this talk at Circle CityCon, a friend of mine that happened to be a foreigner came up to me and went, "Hey, great talk, but what does snake oil actually mean?" So for the foreigners in the room, let me define snake oil. Snake oil is an American colloquialism, and it's based in the days of the Wild West when they would sell these fraudulent tonics that may or may not include snake extract that had very, very little, if any, benefit whatsoever. And carried it on and now refers to any product with questionable or unverifiable content or benefit. So that's what I mean when I talk about snake oil. So, brief scoping here, brief explanation of in history of exploitation. And what I've got is I've got the defensive measures in black and the quote-unquote offensive measures in red. In 1971, we've got the creeper virus. Two guys in Pakistan, literally in a mud hut, developed this thing just because they could, not with any malicious intent, but just they wanted to develop some self-propagating code. And then 1986, Dr. Dorothy Denning comes up with the idea of IDS. And then 86, we get the brain virus. And 87, John McAfee, before he decided to become a South American warlord, develops this antivirus thing. And then, 1991, Los Alamos actually goes through and develops an IDS, and Checkpoint comes out with the first stateful packet inspection firewall. And then 1996, we get Smashing the Stack for Fund-and-Profit. It is not the first time that this topic was written about, but it's the one that most people know. You can still go out there and read Alepht's paper. Just remember it's an AT&T syntax, which is just maddening to me, but there you have it. And then here's kind of an interesting thing. 1997, the Return to libc paper is written. And it gets largely ignored. And it gets largely ignored because the old Smashing the Stack thing still worked. And so it gets, just remember that gets written in 1997. Then, 2003, IDS finally becomes commonplace, right? So it was suggested in 1986, developed in 1991, 2003, finally most companies have this thing. And then 2003, Metasploit gets released publicly and people lose their minds. I think my favorite quote about Metasploit when it came out was, "This is like the ice cream man handing out dynamite to kids." I still use that one. And then 2005, Intel develops the XD bit, which is to prevent what Aleph 1 talked about in the Smashing the Stack for Fun and Profit, but it's only the Intanium servers, right? So these are, this is about as close you get to a mainframe without actually being mainframe. So you only find it in big, expensive businesses. 2006, rise of 64-bit architecture means that we finally have stack smashing protection via the non-executable stack, data execution prevention, and address space layout randomization, which is great. So in 2006, we finally mitigate the stack smashing stuff, and now all of a sudden, right, the offensive folks go, "Hey, that return to libc, that guy was onto something." Right? And so by the time we develop DEP and ASLR, we already have a technique for bypassing it. Shortly thereafter, the next year, we get return-oriented programming, which is really just an extension to the return to libc attack. And so what we get is this nice ping-pong back and forth between the offense and the defense. So the good news is you're all going to be well employed. That's the good news. The bad news is we're going to keep buying products that aren't really going to protect us in the way that we would like them to protect us. So just kind of keep that in mind as we go through this presentation. So why are we here? Most people that work in InfoSec are not computer scientists. Just, straw poll. How many of you have a computer science degree? There's a couple of you. Okay, if you had to suffer through automata and you don't know why, you'll learn why. Don't kill me because I'm going to teach all these folks the salient points of automata in about 35 minutes. Okay? So, why does it matter that most InfoSec pros aren't computer scientists? Well, computer scientists have to suffer through this class called automata. I say suffer because every major kind of has a weeding out class, and for computer scientists, it's automata. It's a very, math and notation intensive course about computational theory and complexity. And that computational theory allows us to very quickly figure out if something is snake oil or not. If you'll pardon the language, it is the ultimate bullshit flag. And you get to throw it a lot when you're talking to vendors. And so recognizing that snake oil and being applied that computational theory allows you to, kind of avoid this conversation, right? So the boss comes in and goes, we can't do the breach thing. It's too expensive, we're losing too much, you got to make it stop, right? And then what happens is, Joe Vendor shows up and says, you need our next generation box full of pew-pew magic proprietary technology, and it's full of ODA detection, and it's going to cure all of your woes. And then people that aren't computer scientists, allow themselves to, hope briefly, and when we go, really, you can detect ODAs? And then we get told, yes, DNC, your email will be totally secure. I made these slides up before that whole thing broke. It was just a happy coincidence, I promise. And then they go off and they tell us about their patented pew-pew and magic sauce and snake oil, and you get those conversations and you're not really sure how the product works. And we'll talk about some of that language. And then we throw a bunch of money at them, right? And the vendor does this with their money. And then, 90 to 180 days later, an APT comes along and there's our network, where APT is defined by anybody that could bypass your magic box full of pew-pew technology, right? It very well may be a 12-year-old with a dial-up modem and an AOL account, but they got past your next generation defense, so clearly they're an APT. So who's been to a vendor page recently and read a product description? Right, let me know if you haven't seen one of these terms. Holy crap, what does any of that mean? State-of-the-art adaptive defense, next generation threat analytic, multi-layer hunt, end-to-end, cyber anything, really. I feel dirty just saying the word cyber. Virtualized, cloud-enabled, threat-centric, digital DNA, big data, software-enabled, and I'm going to pick on Sans here. What the hell is a forensicator? I just want to know. There's the machine learning one, but we're going to get, but this, the first time I gave this talk, I gave a very short version of this talk that unfortunately didn't go well at BSides San Francisco, and it happened to be the same time as RSA. And so I went to the RSA vendor area, and I couldn't have planned it better. I saw what in the wow world? First of all, the marketing people didn't think this out through very well, right? Because I don't know that I can say COIP in polite company. It just sounds dirty, right? Second of all, cloud, somebody else's computer. Unless you're running Novell NetWare, it's probably going to be over IP. So it just seems a little redundant to me. Anybody here running NetWare or IPX, SPX? I'm just curious. No? All right. You still got, don't laugh, I still have WWIV source code in C on a floppy disk. I still got it, I'm that old. So, when I see cloud over IP, the first thing I think is, yeah, cloud is made of servers, and then I look at the vendor kind of like that, right? Because I don't even have words for that kind of language. So how do we get past the marketing speak? Well, we're going to computer science the hell out of it, right? We're going to talk about a little computational theory. So there's this guy, you may have heard of him. His name was Alan Turing, right? And he developed this thing called a Turing machine, which is an abstract machine, a mathematical model, used to prove fundamental limitations on mechanical computing, okay? And something is said to be Turing complete if it's theoretically capable of expressing all tasks accomplished by a computer. This is any computer. I don't care if it's an IBM mainframe. I don't care if it's your iWatch, your iPhone, your Android, your PC, your Mac. This is all computers. And automata is this field of discrete math that studies computers and the problems that can, and more importantly, cannot be solved by computers. Okay. So, very roughly speaking, automata breaks up problems into three categories. There are solvable problems. These are considered easy. They can be solved in what's known as polynomial time. There are intractable problems, which are hard, and there are undecidable problems, which are impossible. And it doesn't matter how fast your computer is. It doesn't matter how much RAM, how much hard drive. You can reuse the entire AWS resource pool, and you are not going to solve this problem. So I'm not going to talk about the easy problems. We're going to talk about a hard problem and an impossible problem. And then I'm going to show you how those are enough for you to tell that you're buying snake oil from vendors. So one does not simply solve an NP hard problem. Okay? So what is an NP hard problem? I'm going to describe one to you. The most famous one is known as the traveling salesman problem. And traveling salesman, or TSP as it's known, is explained this way. Given a list of cities and distances, what is the shortest possible route where the salesman visits each city and returns back to the original city? Seems fairly simple, right? Not that hard. Remember that there's only one optimal path. There is only one correct answer. And that answer is the most efficient. It's not sufficient to be efficient. You have to be the one most efficient answer. And it turns out that this problem is really hard for computers. And the reason it's hard is this. Let's pretend that we have a traveling salesman. You just have 5 cities, right? You have 5 cities. So when you start out, how many cities do you have to choose from? You have 5 cities, right? You can start at any of the 5 cities. All right, I'm going to pick my starting point. I have 5 cities. And then how many do we have left to choose from? We have 4. And then we got 3, and then 2, and then 1. What mathematical function does that look like? It looks like a factorial, right? So it turns out that the running time is factorial. So that is non-polynomial time, right? The number of cities is n, and the running time is a factorial of the sample size that I have. So the running time for this thing seems relatively simple, but it's a factorial time. So let's think about this. If you have to generate the most efficient path to go from New York to San Francisco, there are 19,354 cities in the United States, and you have to try every possible combination in order to get the optimal answer. If you do that factorial, and you do one calculation per millisecond, it takes you 110 centuries to solve, right? Almost 111 millennia. Who wants to hang out for that? Anybody? No? There's always one, right? So a deceptively simple problem. It's certainly easy for me to describe, but there are a lot of calculations involved. So, why do I care about TSP? Well, you care about TSP because TSP is analogous to a lot of problems that we want to solve in computation. Optimal routing, right? I want my packets to get from point A to point B in the most optimal path. Well, that's a TSP problem. Detection of man-in-the-middle or race conditions. That's a TSP problem. Resource use optimization. Search algorithms. Crypto problems. Basically anything where you want optimization is going to be reduced to a TSP problem. Yes, sir? If you don't know the optimal routing, how do you know that you don't have a man-in-the-middle attack? Yeah? Okay, so if solving traveling salesman problem is hard, then solving all of these problems is also hard to do via computation. So right at this point, somebody goes, hey, look, I drove here from wherever, and I used a GPS, and it got me here, and it definitely did not take 110 millennia. So let's examine how that happens, right? So GPS works because it makes a bunch of assumptions on your behalf. And so some of those assumptions make sense, right? You're not going to start, your starting point's going to be right where you are. It's not going to be any of those 19,000 cities. Your starting point is where you are, and it's going to make assumptions that interstates are faster than rural routes, and rural routes are faster than farm roads. And then you're going to tell, don't show me toll roads, and don't show me ferries, and it's going to assume things like loops are bad. And so those assumptions drastically reduce your calculation space. They drastically reduce the sample space, and so you get a workable solution. Notice I said workable. It's not optimal. Well, in the security space, if it's not the most optimized solution, you're going to have type 1 and type 2 errors. That means you're going to have false positives and you're going to have false negatives, right? So who's ever, followed their GPS and they end up with something like this, right? Where it goes, yeah, turn left here and you're looking at a building, right? So that's when those assumptions fail. And it's okay most of the time, because most of us aren't playing Pokemon Go where we're following GPS directions and we can actually look left and see the building, right? So we don't actually turn into it. So traveling salesman is hard, but you can solve it if you make some assumptions, right? Those assumptions have to be good assumptions. But how does that saying go about assumptions? Yeah, I'm not going to say that because I'm being recorded, but yeah, something like that. So if the vendor tells you that they're solving a hard problem, they're making assumptions. You probably need to figure out what those assumptions are. So ask the vendor. So that's a hard problem. Who wants to see an impossible problem? It turns out that the impossible problem is actually easier to explain in theory. Now remember, when I say impossible problem, this means that no computer ever following the Turing model will be able to solve this. Period. It's not a Moore's law or House's law problem. It's not a resource problem. It's not a quantum computing problem. Until we do something fundamentally different than what Turing suggested, we're not going to solve it. So here it is. Given M, a machine M, an arbitrary Turing machine with an input alphabet sigma, let omega be an element of all possible strings. Will M halt on input string omega? Who remembers this from Automata? Awesome. The rest of you are looking at me like this. All right, let me draw you a picture. I'm going to draw you a picture. Here it is. So there's your picture. There's your Turing machine M and your input omega. You're going to compute, and then you've got a decider state. So given the reduction state, if the Turing machine state is decidable, then this is a decidable problem. Oh. No standing ovation. All right. KISS principle. Keep it simple, stupid. Here we go. Given a computer program and input, you will not be able to determine via computing methods alone whether it will ever finish running. So I give you a program, I give you an input to the program, you feed it to some analysis computing machine. It's never going to be able to definitively tell you if the program will finish running with that input. Why is that? Well, let's consider the options, right? So you've got this big analysis computing machine running on, the AWS cloud there somewhere, and you feed it the computer program, you feed it the input, and it finishes. Woohoo, success. But what if it doesn't finish? Well, it might be stuck in an infinite loop. It might be running properly, and it just needs more computing time, and you never really know if it needs more computing time. So you wait an hour and you pull it, maybe it needed an hour and 10 minutes. You wait a week, maybe it needed a week and 1 day. So you never really know, or possibly just haven't accepted the upgrade to Windows 10. I'm not sure, but either way, you don't know why it didn't finish running. You just know that it hasn't finished running, right? So this is basically a logic problem. There's no way to get around this, and it's not a computing issue. I'm always going to be able to develop some program and some input that's going to run a little bit longer than you're willing to wait. Okay. So certain problems are provably undecidable, therefore impossible by computing. And so they're going to require substantial assumptions to be made. Same thing for hard problems. And so vendors are going to come to you, and they're going to tell you that they solved one of these hard or impossible problems. So can anybody tell me what the halting problem is analogous to? Yeah, antivirus. This code is definitely bad. It's definitely malware. Well, if you've got a signature, then sure, it's malware. But if you don't, then I don't know. I can't tell if it's going to halt, let alone if it's bad. So when they claim they solved a difficult problem, right, hard or impossible, let's assume that they have. I'll give you the benefit of the doubt, right? You're all fine individuals. You're InfoSec professionals like I am. And then I'm going to imagine that I can take that vendor solution and I can package it in a chip. Okay? And then I'm going to use that chip to see if I can solve an undecidable problem. And if I can use your proposed solution to solve an undecidable problem, then I'll have a proof by contradiction, because I know I can't solve an unsolvable problem. And if your algorithm solves an unsolvable problem, you also didn't solve your problem, right? So the vendor says, we detect O days. Now, let's be fair to the vendors. I've not heard, actually that's not true. I've heard one vendor actually tell me our new product, our new next generation product solves all O days, finds all O days. Normally, vendors are a little bit smarter than that. They leave themselves out and they say, we detect O days. We want to hear we detect all O days, but they rarely say that. So let's assume that's true. Let's assume they've got this O day detector with this magic inside. And then we're going to put that magic O day detector inside of the halting machine. And I'm going to define all halting states as safe code and all non-halting states as malware. Cool, I solved the halting problem. But I can't. I can't solve the halting problem. And if I can't solve the halting problem, then you can't give me an O day detector. That's just not how it works. So that's what's called a proof by contradiction. Except that, right, earlier this year, right, April 19th, MIT releases this thing saying, MIT builds an artificial intelligence system that can detect 85% of attacks. MIT's got some smart folks. Who believes that? Anybody here believe that? All right, so I got forwarded this like by 600 people. Maybe not quite that many, but you know, I'd given this talk before and I got forwarded this. Hey, look, the MIT guys, they figured stuff out. They're smarter than you are. And I went, okay, yeah, they're smart. I didn't go to MIT. I went to a different school, but let's read the fine print. So I went to the MIT, I went to the MIT homepage because I thought surely the mission is accomplished. I'm out of a job now. And I read their assumptions. And it says it presents its findings to a human analyst, and the human then identifies which events are actually real events and which ones aren't. So I'm just imagining like this big box with blinky lights, and there's like a midget inside of it that like takes a slip of paper and goes, no, this one's real and this one's not. So really, you two MIT, come on. I just can't. But never mind the details, right? Let's just go with that 85% thing. 85% is pretty good. That's a solid B. So let's say 1/100th of 1% of people on the planet can write you one O day a year. Seems like a reasonable number. 1/100th of 1%, one O day a year. So let's look at China, who has 1.35, almost 1.36 billion people. 1/100th of 1% write you an O day, 85% of them are detected, right? So they write 13,500 O days a year. We detect 85%, that's 11,000. That leaves 2,036 unidentified and unmitigated O days a year. And that assumes that we block 100% of known attacks, that those humans that get that input make instant decisions, and they're always right, because humans are infallible. That's why we have computers. So 85% is really not so good. So what about malicious traffic and TCP/IP? I picked on AV. Let's talk about TCP/IP. So those next generation firewalls. How many next generations are we up to? This is actually my third next generation. So we had the first generation, then we had next generation, which were second generation. I can't wait for the next generation. It turns out the TCP/IP is Turing complete. And Turing complete means the halting problem applies. And if the halting problem applies, you can't look at packets and positively identify all bad traffic. You just can't. It's a halting problem. And so that next generation firewall, it's going to make things a little bit better, right? But it's just not a panacea. It's just different kinds of signatures that are going to be bypassed in new and different ways, or in old and known ways. But if that wasn't bad enough, we've got this thing called the von Neumann architecture. So most commercial systems, and there are one or two exceptions, have this key feature in their architecture where instructions and data share the same code space. And on top of that, instructions and data are represented with the same assembly level language. So given an arbitrary hex 41 in x86 architecture, it may be a capital A, or it may increment the ECX register. And every exploit takes advantage of the fact that you're expecting data and I'm feeding you instructions. In the case of return-oriented programming, the instructions I'm feeding you are jump instructions where I'm going to find arbitrary gadgets of assembly code already existing in your memory space from completely legitimate programs, and I'm going to dynamically build my payload on the fly. So even data execution prevention and address space layout randomization, they're not going to stop. They're not going to stop us, and that's just kind of where we're at today. So it's pitch black, and you're likely to be eaten by a Gru. For you old people, there was this text game called Zorik. You should look it up. So here's where we're at. We can't optimize resources because traveling salesman problem says we can't. We can't identify malicious logic because halting problem says we can't. We can't tell if our program will even stop, let alone give us a correct answer, because that's also the halting problem. And it's worse. We can't even tell if what we're reading in memory space is data or if it's an instruction. So anybody want to give up? And the bar's right over there. The bar's right over there. So how do we live with no ODate detection? The vendors will claim they can detect some 0 days using signatures and heuristics, which are really just statistical models, which is fine. The way that they're doing that is they're making assumptions. And they're making those assumptions so they can reduce the problem space so they can give us a workable solution. Again, remember that workable solution is non-optimal, so you're still going to get those false positives and false negatives. So we as consumers of those products, we need to talk to the vendors and we need to ask them, what assumptions are you making? And then we need to validate that the assumptions that they're making are sound and make sense in our operating environment. So let's walk through an example. Vendor walked into my office a couple of months ago and said they have this next generation vector-based algorithm for behavior-based network modeling that can detect all malicious activity on the network. What does that mean? All right, next generation, meaningless marketing term, means nothing, right? It's a null. Behavior-based modeling means heuristics or statistical model, and vector-based algorithm means it's directional. Okay, so is it a valid claim? Absolutely not. They are not going to detect all malicious traffic. Can they detect some malicious traffic? Yeah, probably. Is it useful? I don't know. It depends on your operating environment, but let's see. Let's talk about an ICS SCADA system. Why are we going to talk about an ICS SCADA system? They are a physical system, so there's a computer component and there's a physical component. I don't know anybody that has anything nice to say about the state of security in ICS SCADA. It is horribly, horribly broken. ICS SCADA systems are still learning rules that the PC industry figured out in the early 1980s. They're difficult to patch if they're ever patched, and they're missing traditional defense. So when you look at ICS SCADA, these are all old Motorola controllers, in some cases old ARM controllers. They don't have data execution prevention. They don't have address space layout randomization. They don't have antivirus. They don't have IDS. They don't have any of that stuff that protects us on our Windows and Mac networks. And the protocol, while it's well understood, is still Turing complete. So basically, these ICS SCADA networks are as bad as they're going to get. So let's see if we can make it a little bit better. So what are some protocol assumptions? Well, again, we understand the protocol, but it is Turing complete, so halting problem means we're not going to detect all bad traffic. But ICS is still a fairly robust protocol. We are probably not going to use all of the ICS protocol messages in our own unique implementation. So let's just look for the ones that we're not going to use and cast those out as malicious traffic. I'm also going to make the assumption that my ICS SCADA network is my ICS SCADA network, and so I'm not going to see a whole lot of internet surfing. I shouldn't see any internet surfing. I shouldn't be seeing managed code like Java or Flash or Shockwave or all of those things that get you pwned on a daily basis. And I'm going to assume that I'm not going to have any Pokemon Go on this thing. So those are my protocol assumptions. And then these ICS SCADA have a physical component as well. And so these physical components are pumps and their valves and their pipes and their generators. I mean, these are big honking industrial systems. And those things are engineered to very precise failure tolerances. And they have physical limitations. When they're engineered to work within certain heat ranges, to work within certain pressure ranges, to work within certain speed ranges, to heat up and cool down at very, very precise rates. And so anything outside of that would be anomalous, and I should keep track of that. And then I'm going to make these operating assumptions as well. I've got these SOPs. The industrial process is going to be well understood. Again, these are large, very expensive factories, very large and expensive machinery. And so we have these standard operating procedures and actions, and anything outside of those actions should be anomalous. Now, there are times when we go into emergency response procedures, and that allows us to break out of our normal SOPs, but again, we should know that we're doing something anomalous. And not every component in my industrial complex needs to talk to every other component. If the wrong valve is trying to send a message to the wrong pump, we've got a problem. And so when you put those three operational circles together with your physical constraints and your valid protocol messages and your procedural constraints, it turns out that really this is the space that we need to operate in. That is really all we need to monitor, which is a heck of a lot less space than all of this. So that vector-based, heuristic engine, it might be okay. It might make things a little bit better. So key lessons, almost no security problem of real interest can be solved optimally by automation alone. We're going to need security analysts. We're going to need smart people that read our IDSs and IPSs and understand what's really going to go on. We need people that understand the technology and it can actually make sense of what our sensors are telling us. We can solve portions of these problems by making assumptions and understanding the risk. But when we make those assumptions, we need to understand that there is some inherent risk in making those assumptions. Different vendors are going to make different assumptions. That's actually a good thing for us because I know we've all been hearing defense in depth for a long time, but if you buy multiple vendors and they all make different assumptions, then maybe vendor B can catch an assumption from vendor A. It makes it harder to manage things, I understand that, but it does make things safer and security is not free. Understanding fundamental limits of computing are going to help you identify snake oil. Really, you can get by normally on TSP, von Neumann, and the halting problem. If you understand those three, you can sit across from a vendor and when they tell you that they detect all low days, you can go, really? Halting problem. And if they don't know what that means, tell them to bring you an engineer or computer scientist that does. And automation is great. It's going to help you reduce the noise, but it's just not going to solve the problem for you. So for the vendors, please, please, please be honest in your claims. Send me an engineer or a computer scientist. I have questions. Salespeople are great for touching base with your contacts. They're great for making new connections. They're great for maintaining connections. But if I'm going to spend a lot of money on a product, I want to talk to somebody that can tell me what's under the hood because I want to peek under it and I want to kick the tires. Your assumptions and methodologies, they're not secret sauce. If you need to have your vendor sign an NDA to tell them so that you can tell them how your product works and what assumptions you make, then by all means, I've got no problem signing an NDA, but if you're not telling me these things, I'm probably not going to buy your product. And for goodness sakes, quit selling me marketing speak. I am tired of reading an entire book full of literature and not understanding what your product actually does after it. That next generation cloud-enabled, software-defined, heuristic-based, virtualized, threat-centric, multi-layer, end-to-end, analytics, adaptive cyber defense, cloud over IP pew-pew, not worth the glossy paper it's reading on. And if you think that's overkill, please go read some of these vendor pages. You will get really excited after reading about 2 pages of text and realize that you still have no idea what that product does. So for those of us that buy these products, the vendors actually have some pretty smart solutions, right? But you have to understand what the limitations are. If they're making claims that are too good to be true, they probably are. Ask them how they're reducing the problem space and ask them what assumptions they make, and then more importantly, validate those assumptions. Make sure that the assumptions that they made make sense in your operating environment. Learn which problems can't be solved by computers and which can't be solved easily. And realistically, human operators and hunting combined with defense in depth, it's still your best solution. It's going to be your best solution in 10 years. It's going to be your best solution in 20 years. So the next time a vendor comes to you and tries to sell you Brondo, the Ode mutilator, ask them to tell you again how they solved the halting problem. So with that, are there any questions?
So I think one of the previous speakers mentioned the benefit of combined machine and human analysis. How does that play into the assumptions and help balance out what the machine's doing and improve the overall outcomes.
I absolutely agree. I was actually here for that presentation, and that's actually right here in this slide where I talk about, the good system. What he talked about was automation with a good system. So here's your good system of understanding the assumptions and understanding what the machine's going to decide for you, and then those human operators actually going through and validating what the sensor is telling you. So I absolutely couldn't agree more.
So the idea would be that the machine is acting as a kind of first level filter to prioritize things for the human.
Yeah.
Would that be a way to articulate that?
Yeah, so absolutely the machine is a first layer filter to reduce the noise and allow the human operator to spend time looking at the things that really they need to spend time looking at. The low-hanging fruit, by all means, please let the automation take care of that. And then the people can spend their time chasing down worthwhile threats.
Do humans suffer from the same problems that the machines do as far as the halting problem and such?
Humans suffer from different problems.
Humans suffer from a lot of problems.
Humans suffer from so no, I mean, the human can make the decision that if you haven't told me that this thing is halted by now, I'm not interested in it. A human can make that decision. The machine really can't. The machine can do it if a human tells it to. The problem that humans have is they suffer from boredom, and they suffer from, in some cases, a lack of education and training. And in some cases, they suffer from, most of us, a lack of sleep. And so, again, it's one of those things that the assumptions of the machine and the assumptions of the human operator kind of back each other up because we suffer from different problems. Yes, sir?
Yeah, thanks for the talk. I think you're not really going far enough in your criticism of these products. So I think one big aspect that you haven't mentioned at all is that these products can introduce risks, and these risks increase over complexity. I mean, because what we're seeing with a lot of these next generation things is that these scanning engines become so complex that introduces a whole lot of vulnerabilities. There was some interesting stuff by Tavis Ormandy where he found that some antivirus was kind of emulating what a program would do, and then it would, if it cannot emulate the function, it would call the one from the system, and thereby you could get code execution through the antivirus. And also, like, you're totally right that you're hitting these theoretical borders if you're trying to get a perfect detection, but I don't think you're hitting any theoretical borders to trying to build a system that just doesn't execute foreign code. So my question would be if the whole detection approach isn't the wrong way of going, but instead we should design a system that is secure by design. And I think there's a lot of interesting research coming from the LangSec community, which doesn't nearly get the amount of attention it should get. Yeah.
So I agree with just about everything you said. So as code becomes more complex, and that's any code, it's not just antivirus, you're going to have more mistakes because people write the code. It's funny, when you look at antivirus, they actually use a lot of techniques used by exploit code. So library call hooking and root kernel interrupts and those kind of things. That was all developed originally by malware authors. It's now being used by antivirus firms. A lot of the things that Emmett does for Microsoft, and I'm a big fan of Emmett, but it uses a lot of malware techniques in order to detect malicious code. To answer the other question about the detection, the LangSec is doing some great things, but until I can tell the difference between an instruction and data, because I've got two entirely different memory setups for those, we're just chasing up the wrong tree. As soon as I mix data and instructions, and they're both represented in the same language, I'm stuck. And so now I can't tell the difference between data and instructions, and so your program expects data, I actually feed it instructions and convince the kernel to execute those instructions on my behalf. That's the real crux of the problem with the von Neumann architecture. No, we just need to change the construction and architecture of every computing platform we currently use. But no, it's not unsolvable. None of these. No. I agree with you. It's just a matter of, somewhere along the line we chose to do it this way for a reason. We need to go back and re-verify that, the reason that we chose to go down that path, that those assumptions are still valid. I don't think when they chose to build the von Neumann architecture, they were really thinking about the future of InfoSec. I think they were just trying to think about how do we crunch numbers as quickly as possible with as little hardware as possible. So you're right, this may be a time to go back and re-examine those assumptions. Please.
So I'm going to break up the tech talk with a sort of a soft skills people question related to this.
Yes, please.
So you mentioned about demanding to talk to an engineer. And so I'm just curious then, so again, for tips for people if you have to deal with this. So if the vendor is reluctant to do that, so what's considered a deal breaker? When do you pursue it harder? How do you deal with the pushback if they don't want to cooperate with that? So more like the soft skills, how do you deal with it?
So great question. I have found that as soon as I tell the vendor, okay, I'm done talking to you, I'm not going to consider your product, they're pretty much willing to give me whatever I want. Now, I have had some vendors go, look, I'll discuss this with you, but you need to sign an NDA. Or I'll suggest, look, if you need me to sign an NDA, I'm happy to do that. But normally vendors are pretty good, and once they realize that they're not going to get any further with you, if you're a small business, it's much harder. But if you're a larger corporation, it's amazing what they'll do when there are hundreds of thousands or millions of dollars on the line. And I've never had one significantly push back on that. Not even in government, and that's saying something. Any other questions? Okay, well with that, here's your vendor bingo card to go out there and go through the vendor space. Thank you so much, and I will see you around.
Welcome back to the Ground Truth Track at BSides Las Vegas 2016. I just wanted to take one more opportunity to thank all our sponsors because we couldn't make this happen without them. Please visit their booths out in the chill out area. Let's see, we're live streaming and recording this, so please turn off your cell phone ringers and whatnot. And please don't stand in the back because it's a fire lane. Up next, we have Layla Powell, who is a security data scientist at Panacea.
Thank you. All right. Thanks. Thanks. So I'm sure many of you have heard the term data science appearing more and more in an InfoSec context. And at the moment, as we've heard from some other speakers already, the focus currently seems to be on machine learning. Now, machine learning is a great family of algorithms and can be really powerful, but that's all it is. Unfortunately, we seem at the moment to be missing any coverage of the broader discipline of data science. This can be problematic for a number of reasons. First of all, similar to the talk we heard just before, people can get taken up by the hype of advertising around machine learning and just think it's a magic bullet for all their problems if they don't understand the work required before and after to make the solutions robust. Also, people maybe think that they can just start applying machine learning algorithms ad hoc on data without the experience to handle the data properly. But for the purpose of this talk, I want to focus on one of the other areas, which is the fact that we're not spending any time looking at data science as a discipline means that we're missing out on some of the benefits applying the discipline of data science to InfoSec can actually bring. In the last year, I've been working with financial services companies, trying to help them to bake in a data science approach to their data analysis in InfoSec. In particular, we've tried to help them with a couple of problems. First of all, communicating the data. It can be hard in InfoSec because there's lots of different stakeholders to get everyone to agree on what the truth of the situation is. And in that case, you then lose trust in the data analysis. So today, I want to talk to you about why data science is a discipline and what that involves, and look at how applying data science as a discipline to InfoSec can tackle some of the challenges that I've seen people face over the last year. Okay, so data science is discipline. Essentially, what I mean by this is it's a way of doing things. There are principles that govern how you should do stuff. It's not just a bunch of algorithms that we just throw at things. Data science, like many professions, is often misunderstood. People have one idea of it, but actually when you get involved, there's a lot more to it. And I'm sure those of you that are more on the InfoSec side in the audience can sympathize with this problem. So let's talk about the principles of data science. I've broken them down into three areas. And the important thing here is that they all build on top of one another. So the first one, data exploration and preparation, is required as the foundation for everything else that comes afterwards. So I want to give you a little bit more information on each of these areas. Okay, data exploration and preparation. This involves a series of principles. First one is understanding what questions can be answered by your data set. So if you take any set of numbers, you can look at the distribution, you can calculate a median, you can do anything to it, and some other numbers will come out. But you need to understand what information is contained in the data and whether the question you're asking can actually be answered. The second one is domain knowledge. And this was touched on in the first talk this morning, suggesting that sometimes data scientists working in security might lack the domain knowledge to do the work. But actually, we should be getting this from the data. If we understand and work with the data properly, we can learn what we need to know to answer the questions from the data set. But we have to be careful to do it thoroughly. The next point is taking a look at the metadata. So by this, I just mean data about your data. When we take a set of data, say from a database, we don't just assume all of it's valid. We want to look at the timestamps governing when that record was updated. where it came from. Is it still valid now? Was it relevant 6 months ago? Can we still use it? The next point is around quirks in the data. At some point, whichever database you're reading from, you're extracting data from, was designed by another human who might not have thought exactly like you do. So when you export data and start to work with it yourself, you have to be careful not to make assumptions about how that data is structured, how it's updated, and how it's stored. Otherwise, it can lead to misunderstandings, misinterpretation. Then we need to think about completeness. This is a bit slightly related to the first point, what questions can we answer? We need to think about, if we're looking at a population of users or assets, we need to really think about how well that population is represented in the data set we have. If we only have 10% of our assets in the data set, any conclusions we draw won't really be valuable. And finally, I've thrown in simple stats in here. I think this is often overlooked. People often want to jump straight to some really advanced algorithms. But actually, if it's the first time you've analyzed a data set for something beyond its operational purpose, some basic statistics can be really valuable and reveal quite a lot. And you should probably be doing it anyway to check you understand, you have a feel for your data before you start to do anything else. The next area then of data science is applying the algorithms. Now, you will have heard a lot of great talks at BSides today and tomorrow around some of the specific algorithms, machine learning, other stuff, how these things actually work. But today I want to focus on as I said, the discipline of data science and the things you have to be careful of when you apply these algorithms. The main one I'd say is understanding which algorithms are appropriate for, first of all, the data set you have. So if you want to apply a statistical test or a machine learning algorithm, you need to think, what does my data look like? Some things will assume a normal distribution. Do you have one of those? If your data set is skewed, are you applying the right machine learning algorithm to it? The next thing is your use case. What is the question you're trying to answer? And what is the appropriate algorithm to provide you with the information to answer that question? This is particularly important for the scenario I'm talking about, which is not doing data science as a researcher, but actually working with an InfoSec team in a company. So we can't just look at stuff that's interesting. We have to look at stuff that's useful. So the use case and what we're actually going to do with that afterwards is really important. And finally, the other thing we want to consider is the level of accuracy required. So how accurate a number is appropriate? How much time do we have to reach that solution? We can't say we'll be 90% accurate in 6 months because the InfoSec team we're working with needs something a bit sooner. And finally, on to communication, which is possibly one of the most neglected areas of data science and InfoSec. A few of the principles then of doing communication well is first of all balancing what I've called caveats versus usability. So we'll talk about this a bit more later. Essentially what I mean here is giving someone enough information that they have relevant context for their use case and the decision they have to make, but not giving them so much information that they're completely overloaded and don't know what to do next. Next, we need to look at the perspective on the data that's appropriate for the different stakeholders. InfoSec data has a lot of different stakeholders with different roles and responsibilities, and you can't show one plot to all of them to help them do their job. Then we need our insights to be actionable, something I touched on earlier. When we present results from the data, it needs to be something that someone can do something about. There's no point just highlighting a bunch of bad stuff and leaving them to it. It's not really useful. And finally, we need to be careful that the probability of someone misinterpreting the way we've presented the data is low. So our job as data scientists, and this is what you should expect from a data scientist you're working with one, is to make sure you understand what they've presented with you. They shouldn't just be throwing stuff over the fence and leaving you to get on with it. So I just wanted to jump back to machine learning again briefly to say where does that fit in. So it's kind of in this algorithms section. And what I want you to take away from this slide is that if you're going to apply machine learning yourself, For example, if you enjoyed the first talk this morning, you'd like to have a go with some of those algorithms, and you're actually going to use what you find to make decisions. Make sure you do all this first bit, all the data exploration and preparation. You need to do all that as well, and you need to be able to communicate the results. And secondly, if you're looking at tools, back to the kind of crazy vendor claims again, look at what data they tell you they need to have for their solution to perform as they've claimed. Do they need to collect data for 6 months, 9 months? Which data sets do you need? How clean does the data have to be? Because your solution is only going to be as good as the data it's built on. So today I'm going to focus on the bottom and the top of this tower of data science, simply because there'll be a lot of focus on other algorithms in other talks. And I think often we forget how crucial the foundations are and actually doing something with the data afterwards. So I want to talk through how we can apply these principles of data science to InfoSec, and I'm just going to use the example of vulnerability analysis. So I want to start off with the data bit, if you like, getting the strong foundations. Now, if you're analyzing vulnerability data, simply using the tools that were provided by your vendor, by the vulnerability scanner, so just logging into their web interface or using their reporting module, then you don't really need to worry so much about all this kind of data science stuff, because you're just looking at pre-created plots made by the people that built the database, right? So this should all be fine. It's when you want to do something beyond what you can do in that tool. And I've seen a lot in the last year, people end up exporting stuff in Excel and trying to do additional reporting. And the problem when you do that is you need to have some kind of framework and a way of handling that data. Otherwise you get into all sorts of trouble. So if you're happy with your vendor tool, then don't worry about it. If you want to export the data and do something with it yourself, here's how we can go about that. So starting with the strong foundations. So I want to kind of set the scene with an example problem that I've seen in the last year. So we talked earlier about how there's a lot of stakeholders in InfoSec. And in vulnerability data, there's a lot of stakeholders too. You can have the patching teams, the vulnerability manager, you've got the CISO, you probably need to report up to the board as well. And all those people need to pass on information about what's going on. So suppose your CISO has to report on the vulnerability situation to the board. And they've got a nice trend line here of number of vulnerabilities over time. You can see something's happened, right? There's a big spike. So we know the what, but we don't know the why. Just by showing this plot, if they have to go and defend this in a board meeting and say something about it, from this data alone, we have no idea what's causing this spike. So one of the key points is to make sure we actually measure something meaningful. In vulnerability data, we often start off seeing a number of vulnerabilities reported, whether that's in internal reporting, I've seen that, or you log into your vendor tool, that's the big number, the first thing you see. But there's a lot of complexity in this, so I kind of wanted to walk through what goes into that. So imagine now we're trying to help the CISO understand that trend so they can explain what they've seen, give everyone a bit of confidence so they're not panicking. We're going to have to understand what builds up to make this number. Now, if some of you in this audience might be very familiar with vulnerability data, so what I say next might be kind of obvious. But the point I'm trying to make is that anyone that's not working with a given data set day in, day out, won't know all these hidden complexities. So if you're trying to communicate about your vulnerability data to your CISO who might not have been hands-on with the data, they won't know all these things that seem obvious to you. Similarly, if one of your colleagues that works in a different area of InfoSec, but you guys have got to work together, you might not know all the subtleties of their data. So I wanted to just break this down so we're all on the same page about the kind of complexities that can be hidden in those sort of trends in a basic number. The first thing I wanted to talk about actually was kind of naming conventions. So when I started working with vulnerability data a year ago, I was really surprised that two things were called vulnerabilities. So I know, if you're writing a bit of code, you don't want to call two variables the same thing. Same in algebra, same in a lot of stuff. So it turns out that, as many of you probably already know, a vulnerability is a flaw in software that has a unique CV ID or a unique vendor ID. But then if we're referring to an instance of that vulnerability on an asset, well, that's also a vulnerability. So you get used to this, it's fine, but it's actually pretty confusing. And it sounds like I'm being a pedant, and well, I definitely am anyway, but there is a point to this. I was working with one vulnerability manager, and she would have to go to the CISO and explain the vulnerability situation. And you'd have these conversations where you'd say, right, we've got 32,000 vulnerabilities. But we've got less work than last time because we've actually only got 100 vulnerabilities. I mean, it just sounds crazy, and it's a really hard concept to explain. So for the sake of clarity, I'm going to kind of rename that and call it detections. So vulnerabilities are things with a unique ID. A detection is an instance of that vulnerability on an asset. And this actually makes kind of reporting on it and discussing it with lots of different people that don't work with the data a lot easier. So it's worth thinking about language as well as the whole maths and data handling thing when you're trying to communicate to people that aren't in the weeds of the data every day. So let's start to break down this number. So if you remember from the principles of data science, one of the first things we wanted to get was that domain knowledge. So we're going to start looking basically what this number means. Okay, we've got 32,000 detections. Let's break it down. We've got, say, 25,000 unchanged since the last time we scanned. So that explains the big jump we've seen on our original plot that we showed to the CISO. We've got a bunch of new ones, a bunch of reopened ones. We've accepted the risk on some, so that's gone away. We've closed a bunch. And this all adds up to make that number. Okay, that's fine, but we still can't really do anything with this. So let's break it down to another level of detail. So it now starts to get a bit more complicated. And in the interest of time, since this is the last talk of the day, I'm just going to focus on one branch as an example. Let's take a look at the new detections that have come in. It's a bit easier to read. We'll have some that have come in because we've got newly published vulnerabilities. So you've had, Patch Tuesday, a bunch of stuff has been released. You run a scan, okay, that's all now detected on your machines. You have some, actually, we've seen that will come in because they're from an old vulnerability that's been newly detected on your estate. So maybe this is something from 2012 that suddenly pops up on a bunch of assets. So that's potentially interesting. Now, as we talked about before, a detection is a combination of a unique vulnerability and an asset. So we've looked at the causes related to the number of unique vulnerabilities changing. What about the assets? Well, suppose you're also rolling out a program to scan more of your estate. So you now scan a new subnet. So there's more assets. So now you've got more detections of vulnerabilities. But that's actually a good thing, right? You're scanning more assets. You're getting more coverage. This is a good thing. We're not worried about that. Also, maybe you actually buy some new workstations, bring those online, even an area that was already being scanned. You've got more machines again. So again, this is feeding into this increase, but it's not something to worry about. So I think what we're going to focus on is the first two then, things related to the vulnerabilities. But before we go any further, there's a couple of other things we haven't done, which were from the principles of data science. So let's pause this here and check the validity of our data. So let's look at the metadata. So we had the 32,000 detections, and there's a bunch of timestamps in vulnerability data, which you should probably go in and have a look at just before we continue. So let's have a look when the records in the database that we've exported data from were updated. I've kind of picked 90 days as an arbitrary threshold. This is one of the complexities, actually. It's not clear what the cutoff is. When is data valid? And that will depend on what the use case is, how frequently you expect the data to be updated. But in this case, 90 days seem reasonable. So we'll have most of the detections updated in the last 90 days. So you can say, fine, that's recent relevant information. Keep that. We'll have some that haven't been updated in a long time. And again, I've broken out for you here some of the reasons why, some of the complexity behind this number. So some will be detections that simply haven't been retested. Others will have old update times because the asset they're on just hasn't scanned. And then if we again follow on the left-hand branch, those that haven't been retested, why is that? Now we get down to real kind of practical reasons. Maybe there's been an authentication failure. So some vulnerabilities you require authentication to test them. So if that fails, we can't update the record. Maybe the test hasn't been able to be replicated. You have to replicate the exact conditions to retest for the vulnerability. So if you remove a bit of software, maybe they couldn't do the test again. So there's, again, just the complexity of assessing whether the data is valid and making decisions about what do you do with things that are on assets that haven't scanned. I mean, you don't just want to be deleting information about vulnerabilities. So there's a whole kind of issue around this, what the right decision is. In this case, we were going to focus on the new detections. So we're in this side of the tree diagram, so we were OK to continue. The next kind of word of warning, I guess, is around the data quirks I mentioned earlier. So when you're exporting the data and you see something called last scan date, you think, great, I'll just stick that in my my code, I'll use that, plot some graphs, that'll be fine. Do you really know what a last scan date means? Is it well documented? Possibly not. Is it the last time that there was a vulnerability scan? Or the last time there was a compliance scan? Is it when the scan kicked off, when it finished? Is it when the scan was last authenticated or not authenticated, or the most recent of either of those? You can obviously work this out eventually, but a lot of time people will just take the first thing that seems sensible and go with it. And actually, we had a case where someone was exporting data and had got the wrong meaning for a timestamp, so wasn't updating any of their information. So, I mean, this can be really crucial when you start to do data analysis off your own back. So before we move on then, those are the kind of warnings around other things you need to check. So just to remind you where we got to, looking at new detections to explain that spike in the trend graph for the CISO, and we're going to focus on the things from some of the old and new vulnerabilities. This looks interesting. This appears to explain that spike. So the next thing we want to move on to is how we might actually communicate this. So we're going up to the communication part of data science now. We're not applying any complex algorithms, as I said. We're just getting some initial value from some simple metrics. Now, I think communication has been one of the biggest issues I've seen people face. I touched on it before. There's a lot of stakeholders. They all have different areas of expertise. Someone's dealing with vuln data every day, other people aren't, and the same applies for all the different controls. And it can be really hard to get your message across. So I wanted to kind of take a look at this. It's basically what we call the data flow in InfoSec. So you're going to start off down the bottom with your sort of tactical data. So this will be everything from your logs, your controls. And in our vulnerability example, this is going to be our 32,000 detections. Got 32,000 data points down this end. Then as you move up to sort of operational data, so maybe you're kind of vuln manager level now, that's going to be condensed down. The vuln manager is probably going to be looking at, I don't know, histograms of age of detections, so they can see what needs to be patched next, how they're doing, keeping in policy. So we're going down from 32,000 data points, the area is getting smaller, down to maybe, say, 10 bins in histogram, compressing the data. And then we move along to strategic data. So this is going up to the level of the CISO or even the board itself. And this needs to get even more compressed. In fact, one InfoSec team we worked with had, at the bottom end, they were producing maybe a sort of 15-page report. At the top end, they had a quarter of a PowerPoint slide to explain the whole vulnerability situation in the business. So you really need to compress this as you go along. And it's not just a matter of necessity. It's not just people trying to be awkward, make the data more summarized. It simply has to be that way, because as we go along this chain, we go up the levels of management, the responsibility, the remit of the person at each level gets much broader. So on the tactical level, those 32,000 detections, maybe a patching team. There'll be someone working on the patching team, maybe for Windows, maybe just for the UK. So great, they can have all the raw data. They need it for their job, and that's all they're focused on. When we get up to the top, you'll have your CISO who needs to have an eye on all the controls on their estate across all global regions. She's never going to have time to look at the raw data from all of them. And what's more, it's not her job, right? Someone needs to have made a decision before that. So what data we show someone is essentially based on what they need to do with it. And this is really tricky because it comes down to one important balancing act, which I mentioned as one of the principles at the beginning. This balance between caveats and usability. So you need to provide someone with enough information to do their job, but not so much that they don't have time to look at it or they can't interpret it properly. And I think this is one of the big challenges of trying to get to data-driven decision-making in InfoSec, is this flow of information as it goes up and giving people the appropriate level of information to do their job, and recognizing that not everyone needs to have all the details at every time. So based on that, what we can see is that we need different perspectives on the data for different stakeholders. And what data scientists should be doing is taking some data, analyzing it, and then packaging up the results so that they're really usable for the person's use case they're trying to solve. But when you do that, when you make something really great for one person, it's not so great for the other person. That's okay. But I would say, as a kind of word of caution, if you see some analysis in the press or, I don't know, being shown to someone else in your team that's at a different level, and you think, that's too simple. Where's all the really intricate details? Just think, was that analysis intended for you? If it wasn't, you're probably not going to like it. You're probably not going to find it useful. Probably be annoying. Like, I'd love to see all the all the logs, all the raw details. But the person that's been presented to doesn't. They don't have time to look at it. They need to make a decision. What's important is that people get the right impression of the data, the impression you want them to have. Say, the outcome is the right one. And often by giving people all the information you want to give them, you get the wrong outcome because you've just given them a bunch of logs and they're like, what the hell's this? So effective data science will be pretty targeted, is what I'm trying to say. So let's have a look, going back to the vulnerability example, let's have a quick look at the different views that different stakeholders will have on vulnerability data, so you can see an example of what I'm talking about. So for a CISO, as I mentioned before, they have a broad view. They're going to be looking across the globe, and they're probably going to be comparing how different business units are doing. In fact, they are comparing because this is what people we work with typically look at. So some important differences. We've gone away from raw numbers now. We're looking at vulnerabilities per asset, so kind of a ratio, number of detections to number of assets. Otherwise, when you're trying to compare your different business units, a business unit with far more assets is obviously going to have far more detections of vulnerabilities. So if you look at the raw numbers, the biggest business unit is always going to apparently be doing the worst. So the CISO's job here is to make sure all the business units are performing well. So we look at a relative number of vulnerabilities, we compare across the regions, and we're looking at an overall trend. A vulnerability manager, for example, needs a totally different view. Suppose they're just working in the Americas, so this top bar here. They need completely different information. They need to kind of make sure that patching's being done on time and everything's being managed. So the kind of information they might prefer to look at would be something like this histogram where we have age of the detection, so how long it's been on your estate across the x-axis, and the number of detections with that age on the y-axis. So this is showing them if your patching policy was 30 days, you can see you've got a bunch, as everyone does, way past that policy, and plenty coming up. And then they'd probably also need an actual list of detections to see what vulnerabilities are there, to pass on to the patching teams so they can actually go and do something. And this is all the same data. But there's no point showing this to the CISO or the previous plot to the vulnerability manager. It's important, though, that we can easily go from one to the other. So another of the problems I've seen is that people will have high-level plots, which when you break them down to the raw logs, the numbers don't add up. We seem to have lost some vulnerabilities. Someone's filtered them out. Someone's done some weird thing in Excel, and you can't get from the raw logs up to the summarized view and back down again. And that's crucial. Everyone needs to be seeing the same data. It's just been repackaged, but it needs to be the same. So the next point I want to make about communication is around how it's interpreted. So if you're a data scientist and you're plotting a chart, or you're an InfoSec professional, you use handling data, or you're showing something about your data set which you're really familiar with, it can seem really obvious when you make a plot what it's telling you. But all of us have to be careful that we have to put ourselves in the shoes of the person viewing that plot and understand how might they misinterpret it. And again, if you're a data scientist, it's basically your job to make sure that the audience has a low probability of misinterpreting. So an example would be, okay, I'm going to show an average. So one CISO would like to see average time of the detection on the estate before patching. Nice, quick measure, easy, get an idea, compare the business units. Another one we worked with was like, no, rubbish, I don't want to see that. That hides outliers. Show me the full distribution. So it takes a bit longer to process the information in that, but there is more information contained in it. So the question you have to ask yourself is, if you're going to show someone, in the first case, the average, is that guy aware that it masks outliers? Probably he is. But is he going to remember it? Is it going to be in the forefront of his mind when he has 5 minutes to check the report you've produced and has to make a quick decision on what to do, on which business unit needs to be contacted and told to improve their process? And this is again one of the responsibilities of data science, to make sure that the communication is clear and unambiguous. And it shows us that the way we present data is specific not only to the role of the person, are they patching team, vol manager, CISO, but also to the individual, especially in roles where people come from different backgrounds. So for example, the CISO role, some will be very technical, others might be more from a management background, and they might have different skill sets when it comes to understanding data. So we have to bear all of this in mind. The next principle to apply is that of actionable insight I mentioned. So as a data scientist, when you produce a plot, or as an InfoSec professional when you're producing your report, or when you're being shown something, you should ask, so what? What do you actually do with that now? And remember, again, this isn't about doing data science and research, it's about working with an InfoSec team that actually need to do stuff. So I wanted to take you back now to the original plot we looked at, that trend the CISO was trying to understand. And we saw that seemed to be to do with new vulnerabilities coming in, old vulnerabilities coming onto the estate. Let's see what we can do with that. Let's take a look at a way we can potentially provide some actionable insight. So the trend we looked at before is on the left. We can see there's been a sharp spike in the last month. The CISO needs a reason to go and report to the board. And from the kind of analysis we did before, breaking down all the information, getting that domain knowledge, we saw that it appeared to be linked to the old vulnerabilities being reintroduced onto the estate. On the right, if we look at those plotted out separately, notice we don't plot all those things from the tree, the tree diagram. That would just be, that's too many caveats, right? This is usable. We have in yellow the number of detections coming from old vulnerabilities being reintroduced, and in blue the number of detections coming from newly published vulnerabilities. There'll always be newly published vulnerabilities, but as you can see, this is pretty flat. This hasn't changed markedly in the last month. However, the number of old vulnerabilities has shot up, and one of the ways we've seen that can happen is if you have a kind of out-of-date standard build So you put that back in, it's got old software in it. You suddenly introduce a load of old vulnerabilities and you have to patch them again. So this is actionable. This hints at process. This isn't about patching all the time. It's about looking at other aspects of the data. Where are those vulnerabilities actually coming from? Maybe if we update the standard build, we won't have all this stuff coming in. We actually saw an example with some people we were working with, and an old version of, I think it was Skype, had been rolled out. And you can do this analysis broken down by software type as well, and then you see all these older vulnerabilities coming in. And that's just poor process. You don't want to pass that on to your patching team. That shouldn't be there in the first place. So this kind of insight, this is a pretty simple example, but this is what makes something usable. The plot on the left gives an idea, but it's something like the thing on the right which indicates what someone should do next, right? Go and review your process, go and review your standard build. Yeah.
So are the old vulnerabilities that existed before that are now redetected in your own environment, or just vulnerabilities that have an old age that are newly detected in your environment? There are new vulnerabilities too.
Yeah. Yeah, so you could have both actually, yeah. So the case of the standard build, there would be an old vulnerability that's new on that asset. But of course, you could also have, they could have been detected on your estate before. So when that standard build was up to date, things would have been detected on it, they would have all been patched, and now you're putting them back in, essentially. So yeah, you can have both. Another one of the complexities, right? So that would be another avenue to go down to split this out further. Okay, so I feel like we've gone through the kind of framework of data science, for example, of vulnerability. We've seen the way to approach the data when you're handling it yourself, how to get some insight and the things to bear in mind when you're trying to communicate it. What I wanted to talk about in the last kind of section is going beyond your data set. So all this stuff we've talked about is just for one data set. And that's quite common in InfoSec, right? We have all these siloed tools. We look at this one, then we look at this one. But actually, once you have this kind of framework in place to make sure you're handling data carefully, handling it properly, and people kind of get on board, everyone's agreeing on the picture they're seeing, we can start to look outside the data set. One of the first things we should do next is start to think about the completeness of that data we just looked at. We've done all that analysis, but we haven't checked how complete the data is. So this circle represents all the hosts that we found in our vulnerability scanner database. That's what we use for all that analysis. If we look at all the hosts we have on our estate, represented by this grey circle, what we might find, and probably will find, is that there'll be hosts on the estate that aren't being seen by the vulnerability scanner. And unless there's a good reason, they probably should be. We also might see some hosts in this small section here that are in the vulnerability scanner that actually have been decommissioned, and we haven't cleaned up. No one's cleaned up the database. No one's purged the data. But the main thing we're worried about is this grey area. And the bigger this is, the less confidence we have in how relevant our findings of what's driving vulnerabilities on the estate are. So what can we do about this? Well, we can start to look in other data sets to see, to get visibility on these hosts. Now, it'd be great if there was a really up-to-date CMDB, but in my experience, that's not the case. So we can go to other data sets and use those. So what we've tended to do in the last year is get data sets that will go some way to helping us solve the problem we have, but are easy to access. Often, security teams don't own all their data sets. They could be outsourced, owned by IT. On some systems, logging might not be switched on to a high enough level of detail to answer the use case you want. So you have to be a bit pragmatic and get the data sets that will help you, but you can get quickly. Again, we want to get a quick return on investment so that people can actually do something with this data. So one of the things we've been using is AV data. AV and Vuln are both typically quite easily available. So what you can do then is we can essentially join the data sets together and look for hosts that are in both, which is the overlap. And in the case of trying to get a feel for how good our control coverage of the vulnerability scanner is, look for hosts that are only in the AV data. So this is this section here. And then we can go and see why aren't they in the vulnerability scanner. We also can start to work towards some kind of percentage coverage of our vulnerability scanner as a control. So whenever you look at data from your controls, you should try and understand the percentage of your estate that control covers. If it's a really low percentage, your conclusion is just basically useless. You should try and improve the coverage first, then do the analysis afterwards. So as with all the kind of machine learning hype, it's one of those things that like sounds really easy when you first mention it. Actually, it's really hard to match the data sets together. So in the vuln data I typically work with, you'll have an IP address, but often you won't have a host name resolved. Often there'll be no DNS name resolved. So then in AV data, you want to try and match it. But if you use the IP address, a lot of businesses obviously will have DHCP. So is it the same asset now? You can't check the host names because most of the time you don't have them. And okay, if it's the same IP address and the AV scan was an hour after the vuln scan, okay, they're probably the same. Or if it's 3 hours, or 4, or 5, 2 days, at what point do you make that cut? But you can actually do a pretty good first pass with any host names, NetBIOS names, for example, that you do have in the data. So it's not there's complexities, and that's probably, that host resolution is probably another talk. But you can do a good first pass. You can learn something from this data. And then to learn more, you can get more data. So maybe you can get the DHCP logs and start to see which assets are assigned which IP addresses. And at this point, you're really glad you applied that really solid framework of how to handle data and how to communicate it. Because if you hadn't done it, this is an incredible mess by this point. And the more data you put in, the harder and harder it gets to manage it sensibly. So building up that kind of that framework of data science and applying that to InfoSec data allows you to add more data sources in and build complexity without completely losing all the accuracy and trust in your data. The other thing I wanted to highlight is that once you start to get all this data and you're managing it well and you know what you're doing, why not use it for other things? So we can start to get a bit more context around what's going on with our assets, right? We can start to find, when we were finding hosts in lots of different data sets, we can start to say, how's that host looking at vulnerability data? What vulnerabilities does it have? What's the situation in AV? What else is going on? Maybe what users are logging on? What software is on there? Have we had any alerts from other systems involving that host? So we start to get a lot more context that can make it easier to do some of the tactical and operational work. Another benefit is that if we start to bring in business context information as well, we can move towards having a wider view of security across the business. We can start to make it something that is more relevant for the board. We can get a bit more buy-in from the board, right? Because we're now starting to talk their language. We can communicate better with them. They can give them an overall picture of what our sort of exposure to risk is. So, the takeaway from this talk is essentially that, first of all, data science is more than just machine learning. There's a bunch of other stuff. There's a whole framework for how you can approach analysis. And if we can apply this to the way data is handled in InfoSec, we can improve the trust in and the communication of security data. The benefits of this, for those of you that are working in a tactical operational way, is you can get more context. You can know more about what's going on that might also be important when working out how to prioritize tasks to understand which are the riskiest assets. But possibly the most valuable thing in the long run is that we can start to provide evidence to management, to the board, that demonstrates how the work of a security team is lowering risk and helping the business. At the moment, the situation we're in is if nothing bad happens, then it's okay. So no matter how much work you do, there's no evidence to show what you're doing. Just nothing bad has happened. It's hard to measure nothing, right? So this way, you can really communicate to the board what's going on, what the security situation is, and finally demonstrate all the hard work the InfoSec teams are doing. Thanks.
Hi, I have a question/comment, and you touched on the importance of looking at basic statistics, and for me personally, count is the fundamental stat that I look at first, because that addresses coverage. If you don't have good counts, your means don't mean anything. You can't establish statistical significance. So,
yeah, I think that's absolutely true. A lot of the problems I've seen is people, literally the numbers just don't add up. So people think they have X number of hosts, and you look in the vulnerability data, you're like, we've got Y number of hosts, and then are you meant to be scanning these? Are you not meant to be? You have problems with simply numbers of vulnerabilities, not summing to the total you expect to have, because people are exporting data in Excel and cutting it and changing it. So yeah, absolutely, there's a lot of value. Count stuff first, then try summing it, right? Let's look at a median. You have a much better feel for the data.
the other point is, when you're looking for how people are trying to lie statistics, look for how they exclude data.
Yeah. So the exclusions is actually a big issue, and I think it's something that people often do unintentionally. So people will, I talked about if you're not an expert in a data set, right, and someone presents stuff to you, they might assume it's obvious to you that they've cut out things that haven't scanned in the last 30 days. They've cut out severity 1 vulnerabilities, because who cares about those? We probably should care, by the way, but that's not advice. And they'll assume, perhaps, that it's obvious those things have been done. And as that goes up that chain, as that flows through the level of management, no one knows those cuts have been made, right? And then if that person leaves the business, the next person comes in, they're trying to replicate that reporting, and the numbers just don't add up. They don't know that guy chopped out those older detections or made that cut. So absolutely, I think that once you get this approach working, you need to move to something that's repeatable then as well. Repeatable and automated if possible, because then people can't start cutting bits and pieces out.
You may have already touched on it a little bit, but can you share a couple of common ways that, or common mistakes that you can make when kind of interpreting, analyzing data, potentially arriving at the wrong conclusions because, let's say, for example, certain data points are over represented, and therefore you kind of like, oh, the example you gave was, of course, North America is going to have the most amount of vulnerabilities because they have the most amount of assets. Do you have a couple of other examples that are like really easy to fall into, like traps and stuff?
I think it's a lot of it is just around making assumptions, actually. People will see the example I gave around like the last scan date thing, right? People will be like, oh, well, that's obviously the last time the scan started. And then they'll develop some really nice plot based on that and find out later that was actually the last time authentication failed or something. So it's about testing your assumptions about the data, actually. So if you can actually run a test and see what happens when you change things, test your assumptions. Another example like that we saw was in a database, you would have, when you had DHCP, you would have an IP address used by a Windows machine. You get a NetBIOS name. Then a Linux machine would have that IP. And I would just assume, right, okay, that they're probably going to nullify the NetBIOS field, right? That should be a blank now. No, it stays there. That's how the data's stored. And if you had left that in and done all these plots based on NetBIOS numbers of unique NetBIOS names or something like that, they could be totally wrong just because you've assumed that if you built the database, you would have done it like that. It's actually the really simple stuff that trips people up before they even get to attempting to apply black box machine learning. Like this gentleman said, the count's wrong. Or someone's filtered something out in a spreadsheet and not told you.
Great presentation. You're giving me flashbacks to VM programs, and a lot of the problems we had. But one of the things I had was with communication, and I think you kind of touched on that. So I wonder if you had any lessons learned in two different areas. So I've been asked, when I was doing it for metrics that weren't really very good to look at, like percentage of severities in your environment. So, if you clear out all your level 1s, like you said, your level 5s would increase in severity when actually the security would be decreased overall. So that's one example. And then, and also went like impromptu data. So, taking your data at times of the month may significantly decide how your data looks, like after patch Tuesday or whatever. So I was wondering if you had any suggestions or lessons learned around those two areas. So.
Yeah, I think so to start with the time analysis thing, I think that's something you absolutely have to be careful with. So, for example, one of the things we do when we first go in and start working with people's data is try and match to their existing reporting, right? A bit of validation. And you can find that if you export from a database on a Monday one week and then export on a Tuesday another week, your data doesn't agree. So it's important to bear that in mind. It's also important to think about whether you want to look at behavior in kind of like a rolling window, or if it's the current status that's important. And that depends, everything is quite dependent on what the use case is. So I think it's being aware of that and thinking about how it might impact on your results. Remind me your other...
The other one was on kind of funny metrics being asked for, like, you present your data in vulnerabilities per host, which is an excellent NIST metric, but, I've been asked putting it in a percentage as a pie graph, which is horrible.
Oh, God, yeah.
Beyond just the pie graph.
Yeah.
Percentages is not an accurate way to measure.
Yeah, I think this is the thing. This essentially comes back to the kind of breakdown, right? The vulnerability stuff is you have to see what's feeding in. I think you have to try to guide people. I think just doing data science is sometimes a bit of an education piece. So in the same way that you can take guidance off InfoSec professionals around the way that data is useful to them and what they need to do their job, they can hopefully take guidance from data scientists around the best way to present data. And I think if you explain to people why they might actually be misleading themselves by showing that, and give them an alternative and show them a valuable alternative that's useful. So maybe looking at, like as you said, like a ratio of things instead of percentages. I mean, percentages can be fine. It depends what you're doing, right? The coverage one can suffer as well, right? So, your coverage can be really good and you can bring more assets online, and then it takes a while for the scanner to go and find them, so your coverage plunges. It's about having reasons, about being able to explain the differences.
And how to explain sometimes an increase in vulnerabilities may actually be a decrease in your risk if you added more hosts or...
Yeah, exactly. So that was the tree I had before. That was the point. Some of the changes are actually positive. You've rolled out your scanner to a new business unit, and I've got loads more vulnerabilities. So it's about, I think, there's not one metric, right, that's going to give you the whole state of vulnerability. So it's about potentially having a bunch of simple metrics that are kind of that will flag up these areas. So they'll flag up things around process. So looking at age of vulnerabilities and how that changes, whether they're old or whether they're new. You start to look at, as I said, standard build process or other things. Also looking at tracking the number of assets. So I think one thing I've been working on is actually, as a complement to looking at number of vulnerabilities, is looking at how the number of assets on the estate is changing. And you can correlate that, right? So if you have a set of metrics around assets, you can see if that's shot up, you're going to expect a boost in your vulnerabilities. So it's around grouping together metrics, I think, that inform each other. And for sure it's challenging, because especially with vulnerability, because there's so many factors that come into play. But I think anything is better than the kind of current situation I've seen, where it's typically a number and a trend and no insight at all. Yeah, exactly.
Hi, thanks. You have a great presentation, and having done this for a while, I just have a lot of questions, but I think one of the biggest ones I had was, and ones that I grapple with a lot, is the last bullet you have effectively here. So how do you measure, how do you tell, the business ownership, the leaders, the money people, what risk means to them. Is your definition of risk just lowering the number of vulnerabilities? Is that it? Because the risk to them, I think, is something else, and it has a dollar value associated to it. So do you have anything related to that ties in the entire enchilada?
Yeah, nice phrase. Yeah, absolutely. It's really complicated. For sure, it's not the number of vulnerabilities. Totally agree. That's not the point. I think this is something I'm working on with my colleagues at the moment. Actually, is looking into this in kind of how we can really estimate what risk is. That might be looking at that kind of host-centric risk, seeing how that plays out when you look at your controls across the infrastructure. But I think as a kind of first pass, when we're talking about these basic metrics that I've shown today, it's simply about showing, allowing the CISO to show that if he or she implements a strategy, something happens. So if they roll out vulnerability scanning across more of the estate, they can demonstrate they've done that. We have more visibility. So it's around educating the board on what security is doing as well, I think. So it's being able to show an outcome of work you do. And I think one of the examples of vulnerability that can be problematic is if you take a really simplistic view and you just see an increasing trend. If that CISO, in my example, had gone to the board and been like, oh God, look at this spike in vulnerabilities, people will kind of infer things that aren't true. Maybe they're like, oh, what's the patching team doing? This is rubbish. And actually, you've actually improved coverage of the vulnerability scanner across your estate. You've actually done something good, and it represents as something bad if you have overly simplistic metrics. So simply repackaging the data in a way that gets insight, the proper insight, and gives a reason why things are changing. And the CISO can go and point to and be like, you know what I'm going to show you? Okay, vulnerability has gone up, but that's great because we've got awareness of these now. We didn't know these were here before. That's a totally different story to like, there's a big spike. I've got no idea. So I think it's providing reasons, providing evidence for what you've done, and then eventually working up to I mean, like you say, $1 million question, right? Is getting a measurement of risk to the business. Okay, thanks.
That was great. I'm really glad
thanks.
we really should keep refining it and keep giving